Okay, hello, I'm Tom Burniece. I'm a volunteer at the Computer History Museum, and we're here today with Richie Lary, who was a longtime DEC engineer and programmer, and has some really interesting stories to tell. And I want to let you know, as full disclosure, that I was his boss for a while, so I knew Richie pretty well from the 80s when he was working for me, but we're going to focus on the story from the beginning all the way past that. So I want to start out with Richie. Why don't you introduce yourself a little bit and talk about where you grew up and what you're thinking about early on in life.
Sure. My name's Richard Lary. I was born in Brooklyn, New York in 1948. Grew up in a very classic family. My mom and dad were married for their entire lives. I had two younger sisters, went to the New York public school system, and one of the good aspects of the New York public school system was that they had a series of special science and math high schools. They had art high schools, music high schools, but they had some science and math high schools, and I was mathematically inclined and mathematically talented from a young age, and my parents, who were not particularly technical, but they were bright. My mom had a college education. My father had to drop out of college because of the Depression, but was also very bright. Encouraged, more than encouraged, required my education and my pursuing my educational dreams, which was to go into mathematics. So I wound up at Stuyvesant High School in Manhattan, which is one of the really good science and math high schools in the country. And luckily, I was in the right place at the right time for the first time in my life, first of many. The second time I was in the right place at the right time was that when I was a senior in Stuyvesant, the NYU Courant Institute, which was less than a mile from Stuyvesant, as the crow flies, got themselves a supercomputer. At the time, it was something called a CDC 6600. I'm sure the museum has documents on it, if not a partial copy. It was Seymour Cray's first really big computer, and the Atomic Energy Commission bought it on a grant for NYU Courant, which was an institute of mathematical physics, probably to do research on atoms, probably weapons related. And NYU Courant Institute discovered that they could only use a fraction of that machine. So a guy named Henry Mullish, who was at Courant Institute at the time, he was affiliated with the AEC, rumors were he was affiliated with the CIA, convinced them to open up that supercomputer to high school students. And of course, Stuyvesant being right next door, so to speak, less than a mile away, we heard about it, and a bunch of us started trooping down after school to NYU to use what was at the time the fastest computer in the world. So talk about being spoiled, and talk about being in the right place at the right time. We learned Fortran for that. We never really went beyond Fortran because we were all kind of math geeks, and we'd write mathematical programs in Fortran to figure out prime numbers and do other puzzles and things like that. But it was a wonderful introduction to computing. It was completely unstructured. They provided a big bullpen for us, and we would all kind of exchange ideas and do a lot of one-upmanship. Who could do this better? Who could do this faster? And interestingly, a number of us went on into the computer industry. Surprise, surprise. So I was there. A guy named Steve Rothman was there, who I later wound up working on the VAX architecture with. A guy named Bob Frankston was there, who later became the co-inventor of VisiCalc, the first spreadsheet. I disremember a lot of the other names who went there, but I'm sure they all went on into the computer industry. So that's how I spent my senior year in high school. By the time I graduated high school, I was already an accomplished Fortran programmer, right? And knew a fair amount of math. And as a result, a friend of one of the people at Courant had a little company that did statistical analysis. It was called General Analytics. His name, I'm pretty sure, was John Robbins. And he used to get a lot of government contracts to analyze health data for the Department of Health, and educational data for what was then the equivalent of the Department of Education. I don't think the Department of Education existed then, and demographic data for the Office of Economic Opportunity. And so he hired the lot of us because he could get talented programmers for $2 an hour. Okay, and working at General Analytics was just a continuation of fooling around at Quran Institute, except that this time we had some goals set for us. So the first thing that we did was to write a statistical package that they would use to crunch data for all these government organizations. I got to write something called oblique rotations, which is an arcane statistical technique involving a lot of matrix inversions and things like that. Other people wrote analysis of variance and regression and things like that. And we either would submit our stuff through a remote batch terminal, which was the rage then in the mid-60s. It was basically a card reader and a printer and some kind of hard network connection. Or we would have the use of an IBM 1130 computer, which was IBM's equivalent of a mini computer at the time. It was a small scientific computer, still ran off of punch cards, the standard IBM batch philosophy. And so when I went to college at Brooklyn Polytechnic Institute of Brooklyn, which is now NYU's School of Engineering in Brooklyn, New York, I had actually qualified to get into MIT, was accepted by MIT, had a merit scholarship, but money was still tight, and we couldn't really swing MIT financially. Meanwhile, New York State offered some scholarships, and I could live at home at Poly, so it was a lot easier to go to Poly. Went in there, and they had a computer center with a machine that was a relative of one that we were submitting our remote batch jobs to, which was an IBM 7040, big 36-bit IBM iron, right, scientifically oriented. So we started hanging out at the computer center. I did, and then I ran into a bunch of people at Poly, a lot of whom later moved on to digital or other places in the computer center. Some of them were a guy named Jack Burniece, who later became a computer graphics guy, a guy named Lenny Ellickman, a guy named Len Shustik, who's now on the board of the Computer Museum and one of the people responsible for moving it to California. Some people named Joe Fischetti and Hank Moore, bunch of other people. And there were multiple kind of circles at Poly. The original one started out at the computer center, where there was that 7040. We also had a line, I'm not sure if it was initially or later on, to a time-sharing system called GE Time Sharing, which used a variant of Dartmouth Basic and allowed you to go in on terminals and access their GE 645 mainframe, do stuff. And at some point, we also had a timeshare connection to a system that ran APL, which was Ken Iverson's very radical computer language, right? Mathematically oriented and very geek-friendly. So there was a circle of people around that stuff. And then eventually, after a year or two, the administration at Poly replaced the 7040, which was, they really allowed almost hands-on access to, with an IBM 36050, a commercial mainframe computer. And they decided that as befitting the exalted status of the IBM 360, they would create more of a robed priesthood to do the care and feeding of the computer. And they kind of pushed us amateurs a little bit out of the computer center, behind glass, and we were kind of doing things at a remove, which made some of us unhappy. So we kind of wandered around the school and found in a corner of a EE lab at Poly a PDP-8 that I believe Digital had donated to Brooklyn Poly and was basically sitting there unused. And so we decided to use it, right? We kind of claimed it for our own. It had 4,012-bit words of memory, so that's 6 kilobytes, a massive 6 kilobytes of memory. It had a teletype that had a paper tape reader and punch connected to it. That was the human interface. And it had a single DEC tape, okay? So after a little bit of programming it through the paper tape reader and punch, we discovered why it was sitting there unused. It was almost unusable. So the first thing we needed was some kind of operating system that let us use the one tape drive, and I actually wrote that. We called it the RL monitor. It later became the PQS monitor. Some people continued to develop it after I left Poly, and you can look that up on the web. There's still a guy who develops it and promotes it. His name's Charlie Lasner. He was one of the group, and you can find websites of his about the PQS monitor that used to be called the RL monitor. But it was pretty crude. It had the world's crudest file system. All files were fixed length. It wasn't interrupt driven. It just had a couple of commands. We took the digital assembler, which you used to have to load in binary on paper tape, stuck it out on the DEC tape along with the image of the operating system, and that was basically it. And then, of course, we had to figure out a way to copy tapes, so we created a tape copying utility. The good thing about DEC tapes is the reels were only about this big, and it wasn't some complex vacuum system. It was just 2 reels, and tape ran over a head. So the way you copied tape was you ran this program, and it read from one tape, and then you grabbed both reels, and you yanked them off, and you put them on the table, and you grabbed the other tape, both reels, and you stuck it on the reels, and it would write that, and then you'd yank that off and put it on the table and grab the original one, and you do that about 50 times, and you'd have copied your tape. It was slow, but it worked, right? And this gave us the responsiveness of not having to read your program in on paper tape anytime. We wrote an editor that would read in one of these little fixed size files. Of course, it would fit in the memory of the PDP-8. When I say fixed size, I mean like 4,000 bytes. You could then edit that file and put it out, and then when you went to run an assembly job, you'd list out all the files that concatenated together formed the source that you wanted to assemble, and the quote operating system would sequence through those files and kind of feed them into the assembler, which thought it was reading them from paper tape. And then it would take the output of the assembler and stick it into some other file. So that allowed us to actually do software development without spending your lifetime playing with punch tape. And a bunch of us, as I said, the core there, and I'll probably leave out names, was myself, Jack Burniece, Lenny Ellickman, and a guy named Charles Kamen, who was a graduate student at Poly, and it was kind of his machine. So he wasn't quite as technical as us, but he was included in the group because we had to keep him happy. It was his machine. And in fact, he later wound up at Digital also. It's amazing. A guy named Roy Folk, who was a graduate student, and also wound up at Digital and then wound up out here in the Valley. And so Poly did not offer a computer science degree, right? I was a math major. Jack and Lenny were double E majors. There were some computer science courses offered. At the beginning, I think there were hardly any, and then as we went from 1965 when I arrived there to 1969 when I left, Poly started to recognize that computers were important and got some professors in who could teach computer science courses and had some language courses. No real operating systems or networks or anything like that. So we were largely self-taught. The Poly library had access to documents, and we'd go out and read about the hot languages at the time, which were things like Lisp and Snowball. And so we'd implement them in 6,000 bytes on a PDP-8 with our one tape drive.
Okay, now Richie, I got to ask you, did you ever go to class? What were you doing to graduate?
Okay, this is a little embarrassing. I basically wound up working 60, 70, 80 hours a week on that PDP-8. I lived there. The whole bunch of us did. And of course, I was a math major, and I enjoyed math, so I did go to my math courses. As for the other courses, in my spare time, I had actually joined a fraternity at Poly because I recognized that I was in danger of becoming a serious nerd, and I didn't want to become a serious nerd. So I joined a fraternity, and it was a fraternity of actually fairly bright, nerdy guys, right, who didn't want to be nerds completely. But one of the things that happened is that fraternity, 3 separate people in that fraternity figured out 3 separate ways to get master keys to the school. And so I had access to a master key. And so for my non-math courses, I think I took a double E course or 2 just because it seemed like a good idea. But for the rest of the courses, I cheated. Okay, I'm not advocating that as a lifestyle, but I consider that I got an incredible education at Poly, but it was more of a, I don't know, Waldorf school kind of self-directed thing rather than a curriculum-driven education. In fact, one of the big time wasters, as far as I was concerned at Poly, was a gym class. You had to go to a gym class to get graduation credit, and you can't cheat on gym class. There's no final. So actually, to graduate Poly, I bought an insurance policy from the fencing coach, and in return, he retroactively put me on the team for 2 years. I've never fenced. But this was Brooklyn, and you could do this kind of stuff. It's not the kind of thing I want my kids to be doing unless they found a passion, you know, like I did that wasn't available at their schools. But it's what I did, and it worked out great for me. I don't advocate it for everybody.
It's a great story, and I've heard it before in some pieces, but a lot more detail this time. So tell us how you parlayed that experience from the time you're in high school all the way through Brooklyn Poly, basically becoming an expert in programming and understanding computers, into a job at tech.
Expert's a bad word, because academically, my credentials are actually fairly poor. I did graduate with a bachelor's degree in math. I was in a 4-year master's program at Poly. I had skipped the grade in elementary school, and so and I was in a 4-year master's program at Poly. And I did actually get the bachelor's degree, and I had 28 credits towards a master's.
Okay.
And I never did get the master's. After 4 years, you know, I was done. I wanted to build things. I was building things all the time at Poly. I was one of the, I did most of the work on our Snowball.
What's Snowball?
Snowball was a string processing language, kind of the Perl of its time. It allowed you to do pattern matching and replacement on strings. It was a very powerful language at the time, and it was a non-computational language. It was more dealing with abstractions, you know, strings and text replacement and text searching, so it was interesting. Somebody else did the Lisp for the PDP-8, a full implementation of Lisp in 6K bytes. Some of us, the computer center, which we hadn't completely abandoned, it was just not the center of our orbit anymore, had gotten themselves something called a Stromberg-Carlson 4020, which was a very early graphics device. It was non-interactive graphics. You could go back into the tiny room where it sat, and there was a screen maybe this big, this big, high-resolution cathode ray tube, and right above it was a camera, and the purpose of this graphics thing was to produce microfilm, right? So you could do movies. They'd wind up on the microfilm, but it was no good for interactive graphics. There was no input terminal anywhere near it, so you couldn't play Space War on it or anything. Jack Burniece kind of took the lead in playing with the graphics stuff, and I was his assistant. Lenny and I were his assistants. So in fact, one of the things we did at the time, this is kind of an early example of open source, the University of Waterloo had this Fortran compiler called Wat4, right? Waterloo Fortran. This is, I think, was one of the professors at the school actually suggested that we do this. He said, you're so interested in graphics, Fortran isn't really designed for graphics. Why don't you add some extensions to Fortran to implement, you know, like a vector data type Okay, and then you could have a plot command that would plot a vector on the screen, because that's all the 4020 could do. Put a dot on the screen at a particular point. So in fact, we got the sources to Waterloo Fortran and turned it into a graphics version of Fortran. We called it Wat5 because we were college students at the time. We couldn't think of anything more clever.
Now, which
and actually
Lenny
wound up presenting a paper on it.
Which Lenny are you talking about? Is that
This was Lenny Ellick.
Lenny, okay.
Although talking to Lenny Schustick earlier, I believe he did. He credits me with teaching him how to program, and he said the vehicle for that was the matrix multiplication routines that we needed. He remembers it as being in a BASIC. I remember it as being in Wat5, because if you're going to do if you can add vectors as an extension to the language, you needed to do dot products and cross products, and also you needed to multiply vectors by matrices.
Right. Just to add a little context to that, by way to the video here. Len Schustick is the chairman of the board here at the museum, and just met with Richie for a few minutes before this interview.
And one of the people who was instrumental in bringing it to Silicon Valley.
Absolutely.
So, you know, it was good to have some shared history with him. And then because we had been using this timeshare version of BASIC, and because BASIC was a language that was easy enough, as I said, we never took a course in compiler design. We learned from example from, for instance, Wat4 about how to do compiler design. Mostly I, decided to do a BASIC for the PDP-8 that was an actual compiled BASIC, and so I wrote what became PolyBasic, which was a full, featured BASIC. It had a compiler. It didn't compile into PDP-8 assembly language because that was pretty much impossible. PDP-8 assembly language, I'll get back to that, was a marvel of what you could do with a 12-bit instruction, but it was not easy to generate machine code from a high-level language. So we created a little interpretive language that we compiled BASIC into that was a low-overhead interpreter, kind of a threaded code. If you go back, you'll find it had a different meaning back then than it does now. That took quite a long time. That probably occupied me for most of a semester, along with all the other crap that I was doing. But wrote this compiler. It was a multi-stage compiler. It produced code, and then there was an interpreter that ran the code, and then there was the runtime system that supported the code. And ultimately, when I graduated, that was what I took with me to digital on my one and only job interview post-college, which was Digital Equipment Corporation, was the only company that I would consider working for, because I wanted to work for a company that built such a cool machine. And I brought my resume, which was actually in matrix form. It was machines I have programmed, languages I have programmed in, and there were X's in the place where I had programmed in that particular language on that particular machine, and that was my resume, and a deck tape with PolyBasic on it, and they pretty much hired me on the spot.
Who did you interview with? Do you remember?
So probably my first bosses at Digital, okay, which were a guy named Chuck Conley, who ran the PDP-8 software group, and a guy named George Thesell, who was also involved in PDP-8 software, but also in PDP-12 software. The PDP-12 was a lab machine that Digital built, which was a PDP-8 with a laboratory coprocessor on it that had A to D converters and things like that. And probably with a guy named Lary Portner, who headed up software in general for Digital. Okay, those are the people that I logically would have. I don't remember those interviews. Right? There was also a guy named George Berry, who was responsible for another part of PDP-8 software, and who, in fact, I did eventually work for it at one point in my career.
Do you remember what your first job was there? What you actually worked
on
first?
Well, okay. So my first job was to take PolyBasic, and spiff it up a little and stick it. We decided not to productize it. We decided not to call it DEC Basic, but we put it in the DECUS library. DECUS was the Digital User Society, and there was a lot of code sharing going on there, and so we just made it a freebie to give away to people. Okay, but I should because I'll head on into the digital stuff, and there were maybe a couple of things more about Poly to mention. However, I'm going to sit here and stare into space for a while because I've gotten derailed.
Well, you can fill that back in a little later, but if you do have a couple of more things about Poly, that sounds like one of the more interesting colleges in the country at that time frame, with letting students
Yes, they were
really
either
computers
incredibly lax
right.
or incredibly farsighted in doing what they did, which was to give a bunch of undisciplined teenagers
right.
Access to what at the time was a very expensive piece of equipment. That PDP-8 cost $18,000. Wow. The other thing that they had, and I am much less proud of this in retrospect, in fact, I'm doing this in the Computer Museum, so I may be executed for this, but Poly also had a collection of older computers at the time. The one I remember was a Bendix G15, which was a drum machine, had maybe 4 locations of real memory, and all the other memory was on a drum, and you programmed it by writing an instruction and then also specifying where the next instruction was so that you could optimize your program so that the next instruction would be under the head of the drum, just as this one finished. This was like from the 1950s, and they had several of that ilk machine up in a disused room, which they also allowed us to use as kind of a bullpen. And as kids will do, we developed a game called chair hockey, which involved a basketball and a bunch of rolling chairs with the backs removed. And you'd go sliding around the room, kicking the ball, trying to get a goal. And we broke all the switches off of these ancient museum piece computers because we were from Brooklyn and we had no respect. And I feel much more ashamed about that than I do about cheating on my non-math courses.
I think your apologies are long since accepted.
So, okay, if as things come up about Poly, I'll go back.
That's well worth it, because that's a really rich story. I mean, that's much deeper than I've heard before. So that's
okay. So when I first joined digital, PDP-8s were in production. Digital was working at the time on the PDP-8E, which was the integrated circuit, I think, successor. Maybe the PDP-8I was the integrated circuit successor to the PDP-8, much smaller. PDP-8s were the size kind of maybe a small home refrigerator cut in half vertically, weighed about 250 pounds. Oh, here's a combination DEC and Poly story. After I was at Digital for about 3 years, I went back to Brooklyn Poly on a recruiting trip because I still knew some people at the school and I still had some cachet there, and Digital was very hungry for talent. So I went back to preach about how wonderful it was to work at Digital, which it was, to the new students at Poly, and I brought my checkbook with me because I was going to buy that PDP-8 and take it home with me on that trip because it had basically changed my life. I was going to be a math major, and it wasn't clear how you made your living as a math major. My dad wanted me to become an insurance actuary because he knew that was a career that needed a lot of math. And he was very disappointed when I left before getting my master's, and it took about 8 to 10 years before he finally grudgingly admitted that that I probably didn't do so bad after all. He wanted me to get my doctorate. So I went back with a checkbook, gave my talks, and then went over to the EE department that owned the PDP-8 and announced to them that I wanted to buy it, at which point they informed me that it had been stolen. Somebody had walked out of the school with 250 pounds of historic computer equipment. This was Brooklyn. So anyway, back to digital. At the time, and it turns out this has driven an awful lot of decisions, memory technology had improved, and the cost of memory had come down. The PDP-8 was a 4K machine, is the way the minimum amount of memory you could get on it, and because it was a 12-bit machine, 4K 12-bit words was the maximum amount of memory you could address. A 12-bit pointer only goes up to 4K. It did have a memory extension command set, which would let you manually specify the next 3 bits of the address, so it could technically go up to 32K but memory was so expensive that that was kind of theoretical, except that memory prices started to come down and we started to ship PDP-8s with more than 4K of memory. And we had a really primitive operating system for the PDP-8, quote, operating system, no interrupts. It was more of a program development system. And now that PDP-8s were shipping with more than 4K, we needed a program development system that would utilize more than 4K, that would utilize up to 32K, because if the system could use 32K and the assemblers and the compilers would support 32K, then maybe people would buy up to 32K of memory. So Chuck Conley's group that I was part of was tasked with doing that. And our first idea was to go out and see if there was anything being done at universities. And it turns out that the University of Michigan had a PDP-8 and also had a big IBM 360-67 time-sharing system. And one of the hackers there had built something at the Cooley Labs called CPS, the Cooley Programming System. Okay? And it was something that would use 8K of memory and kind of emulate what it was like to be on a terminal of a 360-67 time-sharing system, kind of culturally compatible. And so they sent me out there to evaluate that, and I went out there and played with it, and it was pretty nice. So we bought it. We actually traded them some hardware for it. It was pretty cheap. And then took the sources back and looked at it, and it just wasn't suitable for us. Okay, everything was hard-coded for a particular hardware way of doing things. And it used 8K, but it couldn't use any more than 8K. And meanwhile, I'd come to Digital, and at the time, Digital's flagship machine was the PDP-10. And I fell in with a bunch of people who were the hardware guys and the software guys. There was a guy who graduated a year before us at Poly named John C. Green Jr., and he was hired by the PDP-10 engineering group. So he was friends with guys like Alan Kotak and Dave Gross and Bob Clements and Alan France. These were all PDP-10 hardware, software designers, a very collaborative bunch of very bright people. They were known as the MIT Mafia because they came kind of from MIT over to Digital as a group. And those of us who went from Poly to Digital, which included myself and Jack Burniece and Lenny Ellickman and a guy named Stan Rabinowitz and a guy named Herb Jacobs, we were the Poly Mafia, right? We were the second wave of college kids who were going to come in and transform the company. So I started hanging out with the PDP-10 guys, and the PDP-10 was an incredibly impressive machine to me. It had time sharing, you know, right? Yeah.
Before we lose this track, you mentioned a number of people I know you really respect a lot.
Yes.
Pick out a couple of those names, a guy like Alan Kotak or something like that.
Right.
And just talk about a little bit about what they were all about and why they influenced you. As you and I both know, Alan was one of the key guys that created Star Wars on the PDP-1.
Well, so interestingly enough, you know, I figured you'd want to know about kind of mentors.
Yeah, right. So who were the ones you really respect?
And Digital didn't really work on mentors because it wasn't hierarchical in that sense, right? You just found people whose style you really liked and whose intelligence you really respected, and then you try to emulate them in certain ways. And Alan, so interestingly, I'll be coming back to this because it'll be piecemeal. You know, my mentors at Digital were guys like Gordon Bell and Alan Kotak, and later a guy named Tom Stockybrand, who's actually a mechanical engineer. But the interesting thing I wanted to bring out about that is Gordon Bell and Alan Kotak designed the PDP-8. Tom Stockybrand designed deck tape. So it's like form follows function.
Yeah.
It's like before I ever knew these guys and knew how bright they were,
you knew what they'd done.
I knew what they had done. I knew their work, right? And either, I don't know if the work influenced me to like the guys. No, they were all very likable. They all projected a certain energy and intelligence. And they were also the kind of guys that if they believed A and you believed B and you were going to be in a room with them arguing whether to do A or B, you'd better have your facts straight around B. You better think long and hard about why B is better, because they had their facts straight about why A was better. Everything was very well thought out. in advance. They were all, I'd say, more systematic thinkers than I were, especially Gordon and Alan. Came from more academic backgrounds. I really was, part of just a bunch of guys who would spur each other on to learn things, right? As opposed to being mentored by computer science professors from the previous generation. So it was those kinds of interactions with these people that caused me to learn, not so much a formal mentoring relationship.
Well, I know for a fact you also won their respect, and you certainly did.
Because we
did
were young,
something with their machine.
We were young hotshots, and the good thing about the DEC culture is there was no resentment from the older guys around the young hotshots. There never really were. You'd go, you go, guy, right? And it was my turn to do that when more young hotshots came up. But and so while we're talking about mentors, I'll do names and we can come back to them. So those guys for sure. Bill Strecker later on, and especially in terms of VAX architecture and other things. A guy named Jega Arul Pragasam, who I don't know if you ever knew, Tom, but I did some advanced development work with him, and he taught me a lot about hardware, because it was a hardware and software advanced development project. A guy named Mike Riggle, who I know you're very, very familiar with. And there'll be more as I go on. And the thing about this was they were all people who had deep technical knowledge and at the same time had a refreshing lack of arrogance around their technical knowledge and an ability to bring the technical truth out collaboratively in a meeting without butting heads and stuff like that, or making the people who weren't at their level feel bad about the fact that they weren't at their level. And I learned a lot from them, not just technical stuff, but also how to deal in a community of people with different technical ideas and different levels of technical skill, and bring the laggards up to speed without making them feel bad, and that the focus is on getting the job done rather than being the smartest guy in the room, etc.
Yeah, I can absolutely relate to that, knowing most of these people, and I know they also could think outside the box.
Yes,
everyone.
And many of them had invented a lot of things in the past and broken with tradition in their own way, and it was a great bunch of people.
Okay.
So anyway, going back, sorry for the big digression, but we used to, in the PDP-8 group, even though I had this little operating system that I did, the PDP-10 had a real operating system with a real file system and real tools. And so I would do most of my development on the PDP-10 for the PDP-8. And again, probably this CPS experience was in my mind because when CPS turned out to be not suitable, I decided that I would take the one thing from them that was really valuable, which was the idea that a standalone mini computer terminal should look just like a time-sharing terminal on its big brother computer. And so I set off to implement a system that would later become OS 8.
Was that a unique idea at the time?
Well, the CPS certainly did it before me. I don't know that it was widespread. There weren't an awful lot of companies that were making interactive computers that spanned any kind of range. I mean, Digital was really a leader in interactive computing. All the IBM computers that I had used, including all the 360s, were batch machines, right? You'd queue up batch jobs to them. The 360-67 was IBM's kind of red-headed stepchild in that regard. And later, the IBM VM stuff was another red-headed stepchild that ultimately caught on, and VMware owes success to. But so I set out to build an operating system that, one, would handle a variety of devices. So it had to have, for instance, loadable device drivers and a formal device driver interface, which my old operating system didn't have and CPS didn't have. Two, would have a real file system, right? Not super real. I had 6K to work with, or 8, or in this case 12K, 8K minimum, 8K words minimum, and would look just like being on a time-shared terminal on a PDP-10. And because I was 20 or 21 at the time, I called it the first upward compatible keyboard monitor, which has an obscene acronym. And we were going to do the same thing for the PDP-9 and call it the second upward compatible keyboard monitor, which had a matchingly obscene acronym, and wound up in the comments of the code. In fact, the DEC library knew that if the code was coming from the Poly Mafia, they would run it through a text editor and search for the obscenities and take them out of the comments and the variable names. And I got the hint and stopped doing that. Jack Burniece started writing his obscenities vertically in the first letter of each comment would spell it out as acronyms, and the text editors couldn't find that. He was, but I just figured it was a losing cause and gave up and cleaned up my act. So what started out as fuck'em ultimately became PS8, the programming system for the PDP-8. It was remarkable in a couple of ways. 8K is not a lot of memory, so the kernel of PDP of the PS8 used 256 words of memory. Okay, that was it. You could use all of memory other than those 256 words. And those 256 words were basically some translation tables that abstracted device names and things like that, and a disk driver. Okay, and one of the things about the PDP-8, and this will come up later, and this was very true at Poly, the PDP-8 architecture, right? And this is no failing on the part of Gordon Bell and Alan Kotak. This is the way you had to do things if you were going to design an architecture for a 12-bit machine. Had some very restrictive addressing, and the machine was organized into 128-word pages, not pages like virtual memory pages, but pages from the point of view of addressing. And if your code fit in 128 words, it was great. And if your code fit in 129 words, it got a lot more awkward, because you had to do this interpage addressing to get the pieces, which would then blow up your code a lot more. So it was 129 words, might as well be 150, okay? And we only had a limited amount of memory. So all of us guys at Poly became very good at taking n lines of code and turning it into n-1 lines of code and repeating as necessary. So when we were writing things at Poly, and then later I had these guys help for PS8, I'd write a version of a routine. This architecture also encouraged modularity. You'd write your code in chunks that would fit in 128 words, which means they'd be small. So we were into modular programming before it became common. The architecture forced us into it. So I'd go and write a routine, and it would be 132 words long. And I'd sit and scratch my head and look at the code, and I'd get it down to maybe 131 words. And then I'd give it to Jack, and he'd sit there and scratch his head and figure out a way to get it down to 130 words. And he'd give it to Lenny Ellickman, and he'd get it down to 129. And finally, it would come back to me, and I'd look at what they did and scratch my head some more and get it down to 128, and it would fit. And then we'd have a routine that worked. Yeah, right?
How long did that all take?
A lot of time. But on the other hand, the result was much improved, and we all became really good at writing dense, fast code, right? And that's warped my engineering design philosophy, because I have a bias towards dense, fast code, and it also kind of reinforced an existing tendency that I had to not so much deal in abstractions as concrete things, right? We used to joke later on when object programming and high-level languages came in, although I use high-level languages these days, that people just didn't understand the value of a bit and the value of a microsecond anymore. So, so anyway, our management, which was very cost conscious, didn't really want us developing an operating system for the PDP-8. So Chuck Conley, who was actually a very kind of meek, button-down guy, I explained to him what I was doing, and I showed him an early prototype. And he went up to management and bold-faced lied to them told them that we were making some modifications to CPS, but because of the limitations that we had found in CPS, it was going to take a little while, a little longer than we thought, to modify CPS into something that digital could offer to its customers. Meanwhile, we'd completely thrown the code away and wound up offering them this thing that I wrote which was called first PS8. And then we changed the name to OS8, not because it had actually grown into a full-fledged operating system. It never did turn interrupts on. It was really a program development system. The reason it changed its name from PS8 to OS8 is that this was around 1972, and Nixon had imposed price controls, wage controls, and you could not raise the price of a product without going through all kinds of federal paperwork. So we changed the name, and then we could raise the price because it was a new product. Okay?
That's a good story.
So anyway, so we did that. Some of the other things I worked at in early days at Digital, you got to understand, at the time, I did have a girlfriend in New York, but I'd only go in there about every second weekend or third weekend. And the weeks that I didn't go into New York, I was working 90 to 100 hours. I lived less than 100 yards from the entrance to the building. Okay, Digital was built on a hill, and at the very top of the hill there was a parking lot, and on the other side of the parking lot were two little houses, and I lived in one of those houses. I rented one of those houses along with, at various times, John C. Green Jr. and Jack Burniece and Lenny Ellickman.
Now, you're not talking about Maynard.
I'm talking about Maynard.
So you were with 100 yards of Maynard?
Thompson Street in Maynard.
Wow.
It was off of the Thompson Street parking lot at the top of Digital. And I would get up in the morning and I would roll down the hill into the mill building, and I wouldn't leave sometimes until the next morning. Yeah, right? Because it was all consuming. It was such fun and productive and satisfying and all of that, because it was early enough days in the computer industry that we could be doing stuff that hadn't been done before, right? And it didn't take a team of 50 to do it, and it didn't take as much standing on the shoulders of giants as happens now, where everybody's building on things that happened before. We could do things in assembly language on bare iron that had never been done before, and it was great.
Okay, now I want to get to the VAX in the next
Sure.
15, 20 minutes, but before we do that, any other stories in that first few years at DEC, from the time you joined it in '69 until you started on the VAX, about the PDP-8, PDP-10, or anything else that makes some sense, or fun stories?
Sure. I mean, I got one or two stories about. So Tom Stockybrand was a mechanical engineer, and he became a friend. He's still a friend. He's 83 years old now, and he still radiates energy, right? He doesn't do anything without gusto, he was kind of so he hated software, right? Because it was complicated, and he hated things that were complicated. And he used to tell software guys, you guys, you always want to 1+ everything. I ask you to do this, and you don't do a good job on that, but you give me 6 features I don't want, blah, blah, blah. And he didn't have a software group that helped him out. When he needed software, he'd kind of troll the halls, looking for people who might be willing to use some of their copious spare time to help him. And so I volunteered one time, and I went over to interview with him. Tom he's a good-sized guy, and he's a mesomorph. His face looked like, at the time, it was chiseled out of stone, right? And he had the heavy brow, kind of Neanderthal, brute look to him. He comes striding into the room, grabs a chair, sets it backwards in front of me, straddles the chair, leans into me and says, "What are you good for?" This is his interviewing technique. Right?
I know Tom well. This is fun. I know Tom well.
Hamina. And I wound up doing some work for him. He had this monstrous high-speed paper tape punch that would do 1,000 characters a second or something like that, and you had to wear headphones around it to block the noise, and he needed somebody to write some software for it to get it to do right, because of course the tape was zooming through there so fast that it could screw up, right? Anyway, so I did some work for him on that, and later, just as an aside, Tom went on became our video terminals guy, and he built a terminal called the VT50, which was kind of a failure. It worked pretty well, but it was a little too expensive and didn't have the right resolution and things like that. And we sold a bunch of them, but then one of the things about Tom is he's always learning. He learned from that and built something called the VT52, which became, I think, the best-selling terminal in the world at the time, and then followed that up with the VT100, which was the dominant computer video terminal in the world. And then he got tired of the, quote, politics in Maynard and moved out to Albuquerque, and I lost track of him until I moved out to Colorado, and then it was only a 5-hour trip, and we'd kind of go see each other periodically, and he's still one of my heroes.
Yeah, I know a number of great stories about him, which I won't get on tape today, but one I want to ask you about, I was always told that he used to...
He is available for a video interview,
we'll
and he'd be a great subject.
We definitely want to do that. One of the stories I was always told, and I wasn't around in the days, that he would canoe into the
yes, so
the mill and go into the windows.
Tom was an alternative energy guy from way back, and an iconoclast from way back. He drove an electric Volkswagen in the 70s, and he liked to canoe, so he'd put his canoe into the mill pond and canoe over to where his office was, where he'd leave the window open, canoe up there, open the window, climb in, tether the canoe outside his office, and leave. And in fact, digital, because we did manufacturing in that plant too, security was sometimes a little obstreperous. They thought they ran the company. And so Tom bet him that he could get into the building anytime without going through security, and they took his bet, and he just canoed up to his window, went up there, and went up to security from the wrong direction, said, "Hi, you guys." And I took a page out of his book later in Colorado by taking the hinges off of doors that were supposed to be locked. Yeah, you were there at the time. You had to support me.
I remember that very well.
But so anyway. Go through the early history really fast. Again, at Digital, it just became another continuation of like learning by doing. Digital decided they wanted to get into the commercial software business. There was a guy, and I wish I remembered his name, but he invented a cut-down version of COBOL called Diebol, Digital's interactive, business-oriented language. He wrote the first compiler for it. Right, and then I and a guy named Stan Rabinowitz, who was another polygrad, and one or two other people were tasked with turning that into a commercial system. So we migrated it over to OS 8, and then I wrote a sort for it, and Stan wrote a field-oriented graphics input that emulated these kind of IBM terminals that that you could only type in certain fields, and if the field required a number, you couldn't type anything but numbers in it, that kind of stuff. And we built something called the Commercial Operating System, COS. Right, which was a variant of OS 8 for commercial users. And that's the very
first digital commercial operating system?
Commercial product. Well, on mini computers, yeah. I think they had stuff. They had a COBOL on the PDP-10 for people who wanted to do that kind of stuff. But in mini computers and commercial were kind of non-intersecting worlds at the time. So it was moderately groundbreaking there. And again, little digression for my sins. After I moved to Colorado, I became involved in a rental company. A place that rented tools and skis and stuff like that. And we wanted to go automate. And we found some company in Kansas that wrote software for rental companies. And we got their software. And it included a thing saying we'd get the source if they went under. And sure enough, they went under. And they shipped us their source. And it was in Diebol. And for my sins, I got to maintain a large commercial package written in this language that I had helped promulgate. So did that, did a real-time system for the PDP-8 and the PDP-8, because early on in its history we decided PDP-10 did time sharing, the PDP-8 should did time sharing. A bunch of engineers at Digital, and I wish I remembered their names because they were all very good, implemented a time sharing system on the 8, and in order to do that, they had to add in the equivalent of a hypervisor bit to the PDP-8 where any I/O instructions would trap down to a kernel.
Just as a reminder, we will footnote some of these names, and if you remember them later,
I'll try to come back
into
with
the
them.
transcript. Because
I have some people I can call.
Stuff.
Friend, right? There's a chain.
Okay.
So And so I built a real-time system for the 8 because I'd never built a real-time system before, and PDP-8s were being used a lot in real time, and it was all ad hoc. So I built something called RTS-8, and I got this great idea, and I used that hypervisor bit, and you could run OS-8 as a background task for RTS-8, so you could do the development for RTS-8 while you were running RTS-8 in the background. And you know, so I got all kinds of experience that didn't come out of lectures and books, but it was like, hey, why don't we do this? I'll go research how to do this, and then go do this, right? And eventually I got involved in some of the PDP-11 stuff.
Okay,
there were
talk
other
about that a
people.
little bit.
There were other people doing PDP-11 software. A guy named Bob Bean, a guy named Brad Miller, a guy named Mark Bramhall, who was really the spark plug behind the time-sharing system for the PDP-11, named Ristus. So I got involved not in a primary role, but kind of in a helping out role there. I was never a primary PDP-11 programmer. The PDP-11 was another Gordon machine. Okay. Gordon Bell machine.
Just so there's a number of people who will be listening to this or looking at the transcript who don't know a lot about the difference between a PDP-8, a PDP-10, a PDP-11.
Right. So,
can you kind of give a quick
so at the beginning of the computer industry, there's kind of chaos around word sizes, right? Most of the machines actually around were multiples of 6 bits in length. The common numbers were 12, 18, and 36, and there were some at 24, okay? And if you're a multiple of 6 bits in length, you'd use a 6-bit character set. The problem with a 6-bit character set is you could hold the capital letters and the numbers and a bunch of punctuation marks, but you couldn't get capital and small letters.
To differentiate, that's not what we call a byte today, which is 8 bits.
Correct, correct. It was a character.
Right.
Okay. And when the 360 came out, and there were other machines from smaller companies. There were Xerox had their SDS series, and a couple of small companies whose names escapes me in Florida and other places also built 32-bit machines and 16-bit machines, and they had 8-bit bytes, and you could do a lot more with 8-bit bytes. You had control characters, you had small letters, you had a lot more punctuation stuff, you had escape characters that would let you get into even bigger character sizes, and it became very clear that that was the way the industry was going. Plus, you could address a lot more memory. Again, a lot of this was driven by memory cost. So Digital decided to build a 16-bit machine, and they were doing it, I think, as I joined in 1969, June of '69, right around Woodstock is when I joined. I missed Woodstock because it was my first week at Digital. I think they shipped their first PDP-11 around 1970, maybe 71. And again, it had a kind of a weird little disk operating system that was very slow. And some of the PDP-11 software guys said, hey, you know, we got this system on the PDP-10 that looks like this, and we got this system on the PDP-8 that's culturally compatible with it, has the same commands and the same file name syntax and stuff. Why don't we do that on the PDP-11? And that's how this system called RT-11 was born. I didn't have anything to do with it. It was built by guys, Bob Bean, Brad Miller, I think a guy named Anton Chernoff, a couple of other guys who were the PDP-11 kind of hacker group.
No, was Dave Cutler involved with that one?
Not initially. Okay. Not initially. He came a little later, and he was more of a real-time guy. So RT-11, despite the fact that it had real-time in its name, was really more of a simple program development system. It did have interrupts. You could write interrupt-driven programs, but it didn't have a concept of multitasking or anything like that. When Dave came along, he brought with him a legacy of designing priority-oriented real-time systems. You know, I'd list him as a list of mentors, mainly because he could code like ringing a bell, you know, and his code was clean and small and fast, and it was all the things I admired in code.
Expand a little bit more about Dave, because he's a key player here in the next part of the story. So tell me a little bit more about what Dave was like, what he did, and the capabilities he had.
What Dave was like. I mean, originally, I think he must have come from a non-interactive programming background.
I think he came from a biology degree or something, or something like that.
He would actually write his code on coding sheets,
right? Which
were, you know, pieces of paper with little tick marks in them, like you see when you got to enter your name on a form that's going to be transcribed into a computer. He would code on something else, and somebody else would enter the code. But he was a great, kind of operating system guy, understood a lot kind of intuitively about how to synchronize different tasks going on in a unit processor, later in a multiprocessor, and had a very real-time approach to things. So if he needed to build something, he'd usually build a real-time kernel for it and then build all the other functions up on top of the kernel. And he was a extremely forceful guy. We used to call him like a drill sergeant.
Right.
Right. And his attitude, he eventually became in a supervisory role, and he had a very, very clean management style. He basically said, if you can't do your job, I'll do your job and my job too. Right? Which is a very powerful way of motivating people.
I heard that many times. Just a footnote here, Dave is probably considered today one of the most famous operating system guys of all time, because he did not only RTS or whatever it was,
and
but
VMS,
he did the VMS
and Windows
and kernel, and he did the NT kernel.
Right. So no, he's stayed, and he branched out. He did some languages.
Right.
He did some languages for digital. He did some CPU design. He's a full spectrum guy. It's just that what he's known for is operating systems.
And he's still working on the Xbox.
And he's still working. And he and I didn't intersect that much because he was always on PDP-11s, right? And I was always on PDP-8s. I got involved in PDP-11s, but in a different way. I'll get into. So I helped out a little, and I do have a story because you said you wanted some anecdotes. So digital, I was helping out on Ristus. And one of the ways I was helping out on Ristus is Digital had just built a machine called the PDP-1170, which was a big address machine, even though it could only address, a single program could address only 16 bits of memory. This thing could handle 4 megabytes of memory, and so you could have a lot of different 64K chunks of memory. It also had what's called IND space, separate program from data, to get around the 16-bit limitation, which we'll get back to later. And I was helping modify Ristus to handle this big address space. And as a result, I spent some time on that hardware. So this guy named Dennis Richie from Bell Labs, who was one of the guys who invented Unix and C, we had a relationship with them because Unix, one of its targets was originally PDP-11s, and we told them about this new 11 we were building. And so he came out, we gave him a manual. He made all the changes to Unix to run on the bigger address space and with IND space. And he came out to Digital to use one of our prototypes to test it out on. And I got to be his minder, right? Met him at the door, escorted him over to the PDP-1170, left him alone there, gave him some privacy while he did his stuff. He did his stuff for 3 or 4 hours, got it to work. I came over, it was time for him to leave. I said, you better delete your files because, you don't want to leave this Bell Labs proprietary stuff on our computers. And he said, good point. And he executes one of these, Linux rm *** recursively commands and deletes every file on the disk. And we leave, and I go back to the machine and I grab a tape drive and I do a physical dump of the disk onto the tape drive. Take the tape drive over to PDP-10, and there was a very sophisticated text editor that we all used called TICO, developed at MIT, and used TICO to search for the copyright statements at the beginning of every module, and basically got a copy of Unix, Bell Labs Unix. We never did anything with it. We never violated that copyright, but we kind of looked at it and looked at the internals and, oh, this is kind of interesting, and this is, kind of new, and we learned something from it. It was lovely. Right? There was a core of about 6 of us who actually went and read those sources for understanding to see what the fuss was about. No, we never told him. We did invite him back, though, to the VAX architecture committee, and I'll talk about that. So anyway, so because I was involved in Ristus on the 11, sometime in early '75, I went down to see Gordon because I had some dumb idea about something to do with Ristus, right? And Gordon was the VP of engineering at the time, or the chief technical officer, one of those titles. And I walk into Gordon's office, and obviously I had interrupted him in the middle of a Gordon storm, where he was thinking about ideas. He had some stuff on the board, and he said, listen, we got a problem. Memory's getting even cheaper, okay? And the amount of memory that we can support on a PDP-11 just isn't enough. right? We're gonna be in a position where people are gonna need more memory than we can provide, and not enough of our system cost is gonna be in memory, you know, and we have kind of a certain ratio of the processor is this much of the cost and the memory is this much of the cost. He said, we gotta go to 32 bits. Right? And so I'm forming a committee and I want you to be on. Okay, right? Again, right place, right time.
So you actually walked in, interrupted.
That's how I wound up on the VAX architecture
Gordon Storm,
committee.
and that's how
I
you got
wandered
invited
into
to
Gordon
VAX?
Bell's office
Wow.
just as he was thinking hard about this problem and getting some passion around it.
All right, now tell me about this team he formed. Who were the key people on it, and a little
Okay,
bit
so
about each.
the people on the original committee, and I'll have to amend this later because I don't want to leave out any names, it's important. There was Bill Strecker, who at the time I think was not long out of Carnegie Mellon, PhD out of Carnegie Mellon, and a very bright architecture guy.
And a very structured guy, right?
Right. There was me because of I had a software background, and this was going to be a machine that was going to be friendly to software. Similarly, there was a guy named Tom Hastings, who was a PDP-10 operating system and software guy, been around a long time. You know, was a generation ahead of me in age.
Also a little bit like you and self-taught, or was he also really
you know,
structured
I don't
academic
know.
kind of guy?
I think so. He may have come out of the MIT community, but he was older than the other guys in the MIT community. There's a guy named Steve Rothman who went to high school with me and was one of the hackers at NYU Quran Institute with me and was a hardware guy. Okay, so we needed a hardware guy on the committee.
But he did not go to Poly, right?
He didn't go to Poly. No, he went to MIT.
So he's an MIT mafia guy.
He's an MIT. He's because he was half a generation removed from the MIT mafia.
Okay.
But he still came to digital, and then maybe shortly after it started, a guy named Dave Rogers joined, who was also a hardware guy, very bright. Later became, I think, the VP of engineering for Sequent.
Okay.
Okay. Later wound up at Compaq, and has had a long history in the computer industry. He later became basically the technical lead for the first VAX implementation. In fact, I think that's why he was put on the committee.
Yeah.
Was he was going to have to build the damn thing. Okay. Gordon came to the first few meetings, right? Set the tone, laid out the strategic imperatives. Okay. But he was usually not involved in the day-to-day stuff. He'd come by, but
So who
mostly
acted as a leader?
mostly we would just find a room somewhere and go sit in the room and have bull sessions.
Okay.
Right? What should the instruction set look like? Interestingly enough, early on, Steve Rothman proposed an instruction set which was radically different than anything that DEC had done previously, and we kind of looked at it and went, well, it's an interesting instruction set, but it wastes a lot of memory, right? And we rejected it. And in fact, what Steve had, I don't think there's any record of what he did, but my memory of it is he was proposing a RISC machine.
Is that right?
And
That's
the world
fascinating.
wasn't ready for a RISC machine yet because memory wasn't cheap enough for a RISC machine because the instructions were wasteful in terms of space and memory was still precious, right? But
Just a historical note.
he proposed a RISC machine and we rejected it.
Had anybody-
And it was the right thing to do at the time.
Had anybody done RISC yet?
No.
That
No.
would have
This
been
was,
unique.
the VAX committee was inaugurated on April Fool's Day in 1975. That's my memory.
April Fool's Day. That's
April
great.
Fool's Day 1975 is when we had our first kickoff meeting, okay? And Steve probably, by the summer of 75, Steve had proposed this as a potential computer. And being a hardware guy, he proposed it because he could see how to implement it in a small number of gates and make it fast.
Yeah.
And we rejected it just because it was wasteful of memory, and that was the right decision in 1975, and by 1985 was the wrong decision. Okay? Just this is the way it happens. And the eventual architecture, after we'd kicked around a whole bunch of things, we started calling outside people in, outside experts. One of the guys we called in was Dennis Richie. Okay, because of C. We regard him as one of the guys on operating systems and languages and machines that would be good to compile languages into because we wanted to make this machine as software friendly as we could. Unfortunately, it didn't go well. And it wasn't Dennis Ritchie's fault. It was we couldn't tell him what we were doing. What we could tell him was we were considering extensions to the PDP-11, okay? And so he took a small view of the word extensions and came up with, you know, it'd be nice if you added this instruction, it'd be nice if you did this, it'd be nice if you did that. But he didn't know that we were looking at a radical rethink of what a PDP-11 was. He thought we were looking at a natural extension. And so it was kind of an awkward meeting with him, not because he's dumb, but because we couldn't open up to him about what we really wanted, at which point, if we could, he probably would have had some much better suggestions. But this was early days. It was a complete secret. They had organized the VAX group, I forget when, but there was something called VAX-A, which was the core committee, which is what I was on. And they were
like
responsible
6 guys on that,
for
right?
creating the architecture document.
Yeah.
Then there was VAX-B, which were guys who were allowed to read the architecture document and submit comments. And you know, they were people with a much broader amount of expertise in the company, but they still got to see this thing on a need-to-know basis because this was hush-hush. And then there was VAX-C, who were guys who knew that something was coming and knew the general shape of it and had to think about how to plan to organize the company around this new machine, but weren't privy to the details, right? And that's how Gordon had set it up, I believe. And so we'd occasionally bring VAX-B guys into it and, you know, talk to them and things like that. But at least in my recollection, the guy who came up with the key idea for the VAX architecture, which was how the instruction set, the ISP, should be organized, was Strecker.
Okay.
Okay? And he built an architecture that was superb at conserving memory because instructions were variable length, so that short instructions would be only 16 bits long, 2 bytes long. And then because there were addressing modes, the same opcode would work on a 2-byte instruction or a 3-byte instruction, 4, 5, 6, you know, things just got more and more complicated. As it turned out, it was a very difficult machine to make run fast because of the complicated nature. You know, in order to fetch the next instruction, you had to figure out where it started. And because this instruction was variable length, as you got more bytes of the instruction, you could finally figure out how long it was. It introduced a certain sequentiality in there. But given the constraints at the time, which was we knew that the first VAX, which had to be a full commercial system with all kinds of bells and whistles, was going to ship with 256K in memory, okay? It was a great architecture for the time. And it was also a great architecture for compilers to compile code for because operations and addressing modes were completely orthogonal. Pretty much every operation, you had an add operation, and you could add register to register, you could add register to memory, you could add memory to memory, you could add memory with indexing, et cetera, right? There wasn't separate opcodes for that. The compilers were a lot easier to write. So we got through the instruction set.
So you're saying that most of that architecture ultimately came down through Strecker.
The core of it, which was the structure of it,
right,
the overall structure of it, came down through Strecker. When it came down to picking opcodes, you know, a lot of us that had more programming experience than Strecker, you know, got to get our oar in, and oh yeah, this is an addressing mode that really cuts the size of the code down, or cuts the number of instructions to do something down, blah blah blah. But the framework for the architecture, my memory anyway, came out of Strecker's head.
Okay.
And he just, you know, kind of got up on the board one day and drew it, and we said, like, that's it. Huh?
Now, just for historical reference, about when you said you started on April 1st, 1975. When
Right.
did that happen? Was it within a year or within a couple months or what?
Well, so we started, I mean, I can't give you a precise timeline. We started in April of 75, and I believe that Ken Olsen announced the VAX to the public with a working model in October of 77. I'd have to go check
I think
that.
that's about right.
Huh?
But when did
Okay.
Strecker's
And so there was a
revelation
certain
come
amount
out?
of overlap. I'd say Strecker's revelation came sometime probably in the late summer, early autumn of 75, after we had been collecting a lot of data and starting to explore alternatives, right?
So
and
about
then we
6 months or thereabouts.
Then we
something
started
like
to
that?
flesh in around that.
Okay.
And then we also had to develop an interrupt structure for the machine, memory management structure for the machine, process structure for the machine, because this machine was going to be microcoded. we could do a lot of complex things. You know, we had instructions for decimal arithmetic, and we had instructions to do locked access to memory, and I think we maybe even had instructions to do process context switching, because it's microcode. Make your instructions as complicated as you want. The microcode will execute it. It was the anti-RISC, okay, philosophy, right? Concentrate on getting the code crunched down and making it easy for the compilers. The instruction set was well received within the company, well received within the industry. The memory management, the hot thing in memory management at the time was something called capabilities, okay, which there aren't any machines right now, except maybe that 64-bit Intel processor that never made it, Itanium, that had capability-based memory to this day. But it was an extension of virtual memory where pages could be marked as to what they would be used for, and there was a little bit of object stuff in it. And we built this very interesting virtual memory system that was kind of recursive. The tables were self-describing, and there was one entry at the bottom of the table that let you bootstrap into the rest of the memory structure.
So was that?
And I probably still have the documentation for that somewhere.
If you do, by the way, I'm sure the museum would love
Yeah.
to see it, but so you're basically saying you had kind of an object-based virtual memory system?
Object is not the right word, but it had a little flavor of objects in it, which is that when you describe the page,
Yeah.
you describe more than just here it is. You describe what you could do with it in certain ways and other things. Cutler, who at the time was a member of VAXB, Dave Cutler, he was charged with building the operating system, VMS, along with a guy named Dick Hustvedt, who came from Xerox, and the two of them were complete opposites. Cutler had a real-time background. Hustvedt had a time-sharing background. Cutler was you know, a bull, right, hard-charging and stuff. Dick was a very laid-back guy who relied on you know, intellectual convincing. You know, just he had wonderful ideas, and not that Cutler didn't, but you know. He didn't rely on the force of his personality so much to project what you should do as to kind of just gently convince you is what you do. They were a really good match for each other. You know, this kind of a team of opposites to build VMS. But after we had circulated the memory management scheme, we were having a meeting. Cutler comes in with a couple of his guys, says, "This memory management sucks. It's way too complicated. I ain't gonna build a system with this as the memory management. It's gonna fall on its face." He gives us a half a dozen reasons. He says, "Me and Dick came up with something simpler." He sketches it out on the board. That's the memory management system in the VAX. That's the virtual memory system.
And what was different about it?
What was different about it was all the capability stuff went out the window. All the fancy bootstrapping went out the window. It was a very, very simple system where page tables for user space wound up in kernel space, which is itself virtualized and itself had a page table so that you could page user pages. You could page user page tables in and out. It was just a very simple, elegant system, and my guess is nobody really missed the features that it cut out of what we did. You know, so it was the right trade-off to do. And that was Cutler doing what he does best, which is getting to the heart of the matter and concentrating on performance. And we'd gotten a little overblown in our ambitions, and he called us on it.
So, from an architectural historical perspective, two of the key decisions that were made by Bill Strecker and by Dave Cutler on how to structure this thing.
On how to structure.
Dave with the memory management, and I guess Bill basically with the overall code structure.
With the architectural framework. Right. The meta architecture.
Okay. Now at that point, Dave was on VAXB, so he wasn't really a member of the
I think
community, but
after
he was
that
close,
we started including him more in VAX-A.
Okay.
Yeah. You know, it's like, oh, you know, if he's going to come up with ideas like that, hey, Dave, come to the meetings.
Now, before I forget it, because he's such an important person, talk a little bit about Hustvedt and what happened ultimately to Dave.
Right.
To Dick.
To Dick. So Dick Hustvedt came to us from Xerox, wound up involved in VMS. I don't want to try to separate out what parts of VMS belong to Dave.
I think he kind of drove the program, though, afterwards, right?
Belonged, huh?
When I joined the company in 1981, I think he was basically in charge of VMS.
It could be.
Yeah.
I think it was more of a shared responsibility. But
Dave was already in Seattle by then.
Yeah, Yeah. Dick, unfortunately, was in a car accident, a very bad car accident. Somebody T-boned him on the driver's side.
That was like 1982 or so,
Yeah,
or 81, because I was already
right.
at DEC.
I was already in Colorado, and it left him brain damaged. Okay, it was damage to the frontal lobe and the parietal lobe. And Digital, to their credit, Digital had an engineering hierarchy that paralleled the management hierarchy. Management, you could be a supervisor, a manager, a senior manager, a vice president, whatever. And as engineers, you could be an engineer, a principal engineer, a senior principal engineer, a consulting engineer, senior consulting, corporate consulting. Right, so Dick had gotten up to being a corporate consulting engineer, which is pretty much the highest level. We later, when we got bigger, we invented senior corporate consulting engineer. But he'd gotten up to corporate consulting engineer, and Digital, to its credit, we listed those in the annual report. They never took him off the rolls.
Right.
His residence became a nursing home, and he was in the annual report every year as a corporate consulting engineer.
I mean, that's a real tribute. Now, is he now passed away, or is he still alive?
I believe he has passed away. But
okay,
I'm not,
but I
I'm
know
not
they
sure.
did this. And
I would go visit him occasionally.
Yeah.
But I lived in Colorado. It wasn't that easy. There were people who visited him regularly, and he had moments of lucidity and moments where he was hallucinating, and but he'd recognize people when they came in, and I mean, it was a real tragedy. It was a major loss.
It really was. It was one of the most, absolutely. And he's probably one of the most revered guys in DEC history when you get right down to it. So talk a little bit more about then Dave and Dick's working relationship. Did they work together on the original coding of the VMS,
I
or
think
did they split it, or how did they do it?
They kind of split it up. Dave was responsible for
He was the kernel guy.
the kernel,
right?
Handling devices, scheduling jobs, things like that, right? And Dick was responsible for the OS services layer. That's my understanding.
That would make sense.
Right, things that reached into the file system and other things like that, right? So the closer you got to the user experience, the more Dick was involved, and the closer you got to the hardware, the more Dave was involved.
Right.
Right. That's at least, as I said, I was at a distance from there, because after I finished on the VAX, I had never done any hardware before. But being exposed, I'd never done a computer architecture before, right? Again, this is learning by doing. After being on the VAX architecture committee, I kind of got a taste for hardware, right? I wasn't ready to do hardware. I didn't know anything about hardware. So I did two things. One is there was a PDP-11 coming out called the 1160 that was microcoded. So I decided to help them out, right? I kind of volunteered and wrote some microcode for them, which is getting right down controlling the gates of the hardware.
Was that your first time actually doing microcode?
That was the first time I did any microcode.
Now differentiate for the audience between microcode and software.
So the software is what the machine presents to the world. Okay, microcode is just an internal technique for designing a computer that's going to do
intimately
complex
manages
things.
the hardware.
It is usually every bit or bit field in the microcode has some direct control of switching some mux, or turning on some gate, or providing controls to an ALU or something like that, right?
Where software's
and
compiled
so
runs at higher
microcode words
levels.
tend to be very wide.
Right.
Tend to be, although later people actually succeeded in doing this, but tend to be very difficult to do any kind of machine translation to. You write a high-level language that converts into microcode. So it was all hand coding, which of course I was great at. And the other thing was that microcode used to fit in a read-only memory, or at least a very hard-to-modify memory. You could do updates to it, which meant you only had so much.
Right.
And this is where my skills at turning n words into n-1 came in handy. Okay, so I became a microcoder on the PDP-1160, helped write some of that code for floating point and some other things. And then as a hack, I wrote a PDP-8 emulator in microcode for the PDP-1160. And a friend of mine who was in Mark Bramhall, who was doing Ristus, built a shell in Ristus that we could run PDP-8 code native on this PDP-11, and it would run at PDP-8 speeds because the 1160 was a pretty fast machine. And the PDP-8 guys who were left, who were still doing PDP-8 development, used that as their development platform. They had a virtualized, emulated PDP-8 that was time-shared, that ran it at PDP-8 speeds, and that they could access, from their offices as a time-sharing system and run multiple jobs on and stuff like that. And they used it for the next 10 years to develop PDP-8 software.
Just as a quick footnote again for the historical record, when I joined the company in 1981 to run the Colorado Engineering Group, which you remember, Gordon made it very clear, who was my boss's boss, I worked for Grant Severes, who worked for Gordon, that you were on call at any time they needed somebody to fix the microcode.
Yeah.
And you were considered the microcode fireman of the company.
Yep.
And you would be called and you would leave Colorado and go get into somebody else's spaghetti code and fix it and then come home.
Yep, in fact,
and you did it all the time.
I wound up working on the microcode for one of Tom Stockybrand's terminals where they were run out of space. When the original VAX was done, the VAX 11780, they had 4K of ROM for microcode, and they had a small writable control store in case that overflowed, and they started to run into space trouble on there. And so I joined the project temporarily and kind of crunch, made it, wrote negative code.
Right.
Right. Took 100 words of code and turned it into 80 and kept doing that in other places. And then I wound up implementing some of the, the weirder decimal instructions and other things. And it helped, it helped us. The more room we had, the more stuff we could pack in. So yeah, I was a code bummer, right? I don't claim to be a great theoretician or abstract shrinker, but boy, abstract thinker. But I was an abstract shrinker. I could bum code.
There's no question about that. Your legacy is definitely there, among other things. Let's talk a little bit more. We're going to take a break in a little bit. Let's talk a little bit more about the VAX team and let's say the implementation of the VAX, how it happened, who the key players were in actually implementing it, and then we're going to kind of move into the VAXcluster after a break. But tell me about how that whole VAX architecture turned into a product. So, who are the key guys that made it happen?
Okay, and here I'll have to, there are a lot of names that I'm going to have to refresh my memory on, right? But the guys who pulled it all together, okay, there was a guy named Peter Conklin,
yep,
who unfortunately died young of pancreatic cancer, I think. But he was effectively the program manager, I think. He kept all the balls in the air.
So he was the overall program manager of the VAX.
This was an immensely complicated program. We had new hardware, new software. We had a field to train. We had manufacturing to get going, and he was where it all kind of came together. The hardware effort was run by Dave Rogers, coming out of the VAX, out of the VAX A committee into his job as the hardware development manager. He had a lot of help, and these are the guys. Some of the guys I remember on that project was a guy named Judd Leonard, who actually came out of the real-time PDP-12 kind of laboratory stuff, became one of the firmware developers. I think there was definitely a very, very competent hardware engineer named Bob Stewart. I don't remember how much of a role he played on the 780, but he played a role in one of the follow-ons. At the same time we were doing the 780, we realized we needed a family, so Steve Rothman came off the committee and became the lead for what became the 750, the smaller brother of the 780, which was about a year delayed in time, but he started putting a team together around that. The software effort, as I said,
on the hardware side, Bill Demmer was in there someplace.
Bill Demmer was in management. Yeah, he was a senior manager, but I'm talking about guys who
did the implementation,
lived it, right? I mean, Bill certainly lived it, but you know what I mean. He was a people and budget manager, not to denigrate people in budget management. It's incredibly important, but in terms of the technical project, right, getting all the pieces to come together at the right time, et cetera. It was guys like Peter Conklin. The software, had some strong personalities in it, like Dave Cutler, et cetera. It was led by a guy named Roger Gourd. Okay, Roger has had a career since then, but he was the kind of guy who could keep strong personalities on target and not working at cross purposes, and he was very, very effective at that. I still have a little note that he wrote. There were a bunch of us names I've mentioned before, myself, Stan Rabinowitz, and George Berry. This is a little side thing. Every computer that Digital had ever produced had a code card, which was a single piece of cardboard that an engineer could stick in the ubiquitous, shirt pocket, okay? And you could pull it out, and it would have the architecture of the thing, what the instructions were, and how to do it.
Talking about like a 3x5 card with the architecture.
It was a cheat sheet. It was more like a 3x8 card, okay? Well, the VAX was so complicated that nobody, the idea of a code card was ridiculous, okay? However, George Berry, who I originally worked for at Digital in PDP-8, had gone on to become the head of the Typeset 11 group. Digital had gotten into the computer typesetting business as a little side thing, setting type for newspapers and classified ads and stuff. And so this was the first kind of non-WYSIWYG, but real editors that would do real kerning of fonts and all that kind of stuff. And I don't know who had the idea, but between Stan Rabinowitz and George Berry and myself, it was like, we could do a code card for the VAX. It would be an accordion, okay, but it would fold down to the same size as the regular code cards. And so we just came in over a weekend and came in on Friday night, and by Monday morning, we had it done. George provided the technical support for Typeset 11. Stan and I did the front labor of laying everything out. And we handed it to Roger Gord on a Monday morning. And he almost kissed us.
Did that become then his managing document?
Because it wasn't in anybody's job. Nobody had signed up to do this. It was like, hey, Roger, here's a present for you, right? And boom, he went and had a gazillion copies printed, and all these guys now had something they could stick in their shirt pockets that was the cheat sheet on how to write code for the VAX, because VMS was written in assembly language.
Now, when you talk about Roger being in charge of the software, you talk specifically VMS or actually beyond that? In some of the other
everything.
pieces?
He was the software manager. Is my memory. Yeah.
So somewhere down in there, we got Husfit and Cutler.
Yeah, they were the technical leads, the project leads, for it. But he was the guy who pulled all the software guys together and made sure that the operating system and the compilers and all that other stuff was going to all get there at the same time and all work together and work well together, and the interfaces were going to be long-lived and all that. So he had architecture guys working for him and a lot of implementers working for him, and he was kind of the Peter Conklin of the software side. Huh?
Yeah, almost the equivalent of the Fred Brooks on the Systems 360, right?
Yeah, exactly.
Who wrote the Mythical Man Month about how hard that was.
Right.
Did you have similar problems? Or did Roger keep the size of the team down and make it efficient?
We went in 2.5 years from Gordon calling a meeting to announcing the product. That's pretty damn good.
How many guys?
You didn't have a lot of slip-ups in that kind of thing. There was a very early on, the hardware team built a breadboard, which was, I think, called the VAX breadboard. It was like a 1/10 speed version with wire-wrapped cards and a lot of discrete components, and it was slow as hell. And the software guys developed the software on that until the real hardware was ready. We didn't use, I think, any custom chips on the VAX, but we were using chips that were going to be available when we needed them, not were available when we started the project. So we were laying things out and laying boards out and then waiting for certain chips to arrive that were necessary, that were the fastest SRAMs we could buy at the time and things like that.
This is the middle 70s.
This is the middle to late 70s.
TTL or ECL or something unique?
It was all TTL. The 1170 and the 1150 were all TTL Schottky, S-series TTL logic. Later we built something called the 8600, which was ECL.
Okay.
Right, and in fact, Judd Leonard went on from playing a supporting role in the 11780, is my memory, to being basically the lead firmware guy on the 8600.
Okay.
But when the architecture part was through, I kind of went back to PDP-8s and PDP-11s, and in fact, I was, VAX stood for Virtual Address Extension. Okay, meaning address more than 16 bits, okay? And I was so impressed by all that I went back to PDP-8 land. And I said, memory's getting cheap. instead of having a 3-bit extension to the PDP-8's 12-bit address that got you up to 15, maybe we ought to add another 2 bits and get you up to 17, and we actually made a VAX for the 8, you know, right? All it did was extend the memory. And in fact, Tom Hastings kind of went back to the PDP-10 guys and said, you know, we only address 18 bits of memory. We need some kind of address extension for the 10, got the hardware guys involved, and they figured out a way for a program to address more than 18 bits on the PDP-10. So we went and did the VAX, and then we took that religion back to our old groups, and we came out with 128K word, so about 192K byte, PDP-8.
What was
right?
the model number of that?
Huh?
You remember the model number of that?
No, I just remember the poster for it, which was a picture of a PDP-8 with an elephant standing next to it with its paw on top of it, and something about memory only an elephant could learn.
I love it.
Or whatever. You know, so the VAX, you know, Gordon's idea behind the VAX infected parts of the rest of the company. It was like, oh, cheap memory is coming. We got to do something about this, right? It's interesting how a concept spreads, right? And at the same time, I got involved in an AD project working for a guy named Jega Arul Pragasam. And that was when I got to, instead of watching hardware get built at a Resolve, I got to get intimately involved in the building of some hardware, which helped me out a lot when I wound up joining the storage group, and we had to invent a bunch of hardware and a bunch of software that all worked well together. Okay, so one other story, and this will probably take us to the break, about the VAX. Again, Stan Rabinowitz, who was one of the Poly Mafia, was another mathematician, right? Much more talented than me at mathematics, and a very inventive guy. And he and I had this idea before the VAX existed, that we thought we could build a program software for a computer that would let it play Scrabble. Okay, there were lots of chess programs and checker programs, right? But Scrabble was a different kind of program. It involved word making and things like that. And it did have some strategy aspects, but mostly it was about figuring out a way to do these kind of searches that weren't really searches for words, but were searches for words with wildcards, and figuring out how you might be able to make words from this crappy bunch of letters you have and this crappy bunch of letters on the board. And we worked out some algorithms, and we wrote a Fortran program, ran on the PDP-11. And it was way bigger than the PDP-11's memory. So it had to do a lot of paging in from disk. And this was all in our spare time as a hack. And one of the questions you would put on your little sheet was, well, what are you most proud of that you did at Digital? And there's a lot of things that I did at Digital that I was proud of. But one of the things I'm the most proud of is the Scrabble playing program, I'll tell you right now.
Wow.
Okay, because it was good. And we published it, and we got a lot of flack. We got flack in 2 ways. One, we got flack from the managers of the tech writers, because the tech writers were wasting all their time playing Scrabble. Because they were English majors, right? So, and this program was good. It was a great word maker, you know, and had some strategy stuff to it too. The second place we got flack was we wanted to release this program to DECUS. Again, free to the DEC user community. And we talked to some people, and they said that was a good idea. And then somebody said, maybe you should talk to the lawyers, because I have a Scrabble board here, and it has this copyright statement on it, Selchow and Ryder, copyright. And so we went to Digital's chief lawyer and said, this is what we want to do. And he said, well, let me see what I can do. I'm going to write a letter to Selchow and Ryder. He writes them a letter. And somebody at Selchow and Ryder must have been forward thinking, because they wrote us a blistering letter back. Don't you dare, right? And when I say forward thinking is, I mean, this was 1976, maybe, 76, 77. Computers were for grown-ups. Computers were for big companies. Right? Who cares if somebody wrote a program to play? These guys, were looking ahead to the point where maybe there'd be a handheld game that would play Scrabble, and they could not lose their copyright to a computer version. So they shot that down. So it became an inside the company only, and then of course stuff leaked out to the user community, but digital could never be formally associated with the release of the Scrabble playing program. But when they decided to announce the VAX, October of '77, Ken Olsen held a big press conference, right? Not just the technical press, but the Boston Globe and the New York Times and all this stuff, announcing digital's new computer family to the world. We ported Scrabble to the VAX, where it did fit in memory, okay? And he showed it at the announcement. He said,
oh, that's
you know, people have programs to do chess and checkers and these other games on a computer. Ours plays Scrabble. And he let the press at it. And of course, they're English majors too. So they loved it. They're sitting oohing and eyeing over the moves the computer's making.
I'd never heard that story. That sounds like a good story for the break. Okay, we're back, and we left it with the end of the VAX
the
architectural
of the VAX.
Study, and you're now and beginning the implementation, and you're now back in PDP-8 land, taking some of those ideas into PDP-8 land.
Right.
Now I want to bridge you into storage. The rest of your career was mostly storage, so how did you get involved in storage, and how did that eventually evolve into the VAXcluster and all that? So
okay.
Go for it.
So as usual, it was a right time, right place, this time in a negative sense. The VAX got introduced in October of '77. At that point, they didn't need me to bum the microcode anymore. I was doing some this advanced development project and some PDP-8 stuff and some PDP-11 microcode. And in February of '78, a blizzard hit the Northeast. Famous Northeast blizzard of 1978. Basically closed Massachusetts down for 4 days. I was housebound for 4 days. And shortly after that, in maybe March of 1978, a guy named Barry Rubinson, who I'd known, who was around, who was in the storage group, said, how'd you like to get out of New England? I said, boy, that sounds good to me. And he said, well, we're opening up a storage organization in Colorado. And we're looking for people, and I'd like to steal you and get you involved in the storage group. So you got to leave what you're doing with CPUs and operating systems and all that stuff and get into storage. I said, sounds good to me. And so I went out for a look-see trip in April, I think it was, of '78, and in August of '78, I moved out to Colorado. And in the time in between, I was working with this advanced development group that Barry was part of under Mike Riggle,
right?
Exploring different concepts in controlling storage, okay? So at the time, storage was dumb. Mainly, disk drives. There were lots of disk drives, but generally what a disk drive presented to the outside was an interface almost directly into the heads and the motors of the drive. You'd issue it a low-level command by writing a register saying, seek to this spot, or turn on the read gate, or turn on the write gate, and it would do that. And the controllers weren't much smarter that did that. They would just issue those commands and then act as a conduit for the data to run into the computer's memory to and from the disk drive. And at the time, microprocessors were coming on board, not so much the 8080 kind of microprocessors, which were wimpy, but the microprocessor that we were interested in was a microprocessor called the AMD 2901, which is a bit slice microprocessor, and it was fast. It could run, in the 5 to 10 MIPS range, right? 5 to 10 million operations a second, and it was kind of semi-microcodable. It was somewhere between microcode and assembly code in terms of its programmability. And so Mike Riggle's group under Barry had looked at the idea of using microprocessors in that class to add intelligence to the storage controller itself. And that intelligence would be scheduling operations to the disk, being able to handle lots of operations ahead from the computer, organizing them for best performance, sending them to the disk drive, getting the results back, handling the errors automatically, providing the idea of a perfectly good disk, relocating bad blocks as necessary, all the things you had to do to make disk technology really work, because whenever disk technology threatened to become too reliable, they just cranked the density up until it was on the hairy edge of unreliability to get the cost per bit down. So all that was none of my doing. That was Mike Riggle and Barry Rubinson and those guys. But I came in kind of as an implementer to try to make it all work. The other idea that we had at the time was the idea of using caching, which was a technique that had been developed for CPUs in the early 70s. Turns out the first CPU that had cache on it was actually a big IBM 360. It shipped in December of '69. So really the 1970s were the era of caching. And we shipped computers with caching starting around '73, '74, and we were designing our VAXes that had caching, and we were designing even some systems with what were called write-back caching. And the idea of using caching to speed up storage accesses using DRAM as a cache for storage systems was very attractive, especially caching writes, which was where the real action was, because operating systems, even then, would cache reads, right? But nobody cached writes, because if your power failed, you lose your data. Well, we figured out we could put batteries in there and do other things, right? So the goal was to build a disk system that was intelligent, that could handle a bunch of drives and do the right thing, and eventually the word RAID didn't exist at the time, but do shadowing is what we called it, which is now RAID 1. Nobody had RAID 5 at the time.
It's actually called mirroring today.
It was called mirroring today. It was called shadowing. Shadowing then. Shadowing is different meaning today. Technically it was intriguing, and Colorado was real intriguing. So I said, yeah. And so I moved out to Colorado in August, I think it was, of '78. At that point, Digital was in the process of building a huge plant in Colorado Springs, Colorado. They had bought a little valley. They had gotten some concessions, tax concessions and other things from the city of Colorado Springs in return for some concessions about not being too noisy, not being too high, not emitting too many noxious byproducts of disk manufacture. But we were in temporary quarters at the south end of town. I was not on the first wave.
You were down at Fountain.
Of people to come to Colorado Springs. By then, Fountain had, the original plant in Fountain had been superseded by having 2 or 3 floors of a building on the south end of Colorado Springs itself, an area called Garden Valley.
Okay.
Barry had been busy recruiting a team of good engineers, some of them out of Digital in the East, some of them out of California. One of the reasons Digital established, my understanding, because I wasn't involved in these decisions, but Digital established its storage group in Colorado Springs for 2 reasons. One was that if you built disks at high altitude, they wouldn't crash so much when you took them to high altitude, okay, because the heads have to fly, and if you build them at sea level, the heads fly lower at high altitude, you got less margin. The other reason was some of the incentives that Colorado was offering, and Colorado Springs happened to have one of the first number 5 ESS phone systems in the nation, so it was great for communications with the rest of the country, and we established a support group out there, so the storage group kind of had a home along with the support group. But one of the other reasons is that Digital at that time, late 70s, had gotten so big we had exhausted the talent pool in Massachusetts. We had pulled all the people from MIT that were going to come from MIT. We had pulled all the people from New York that were going to come from New York, and it's real hard to get engineers to move from California to Massachusetts because of climate and other things. But you could get engineers to relocate from California to Colorado because it was Colorado, Rocky Mountain High, and low taxes and outdoor life and no crowded freeways.
Let me add a footnote to that, because I do know some of the backstory here. one of the key reasons that they end up locating in Colorado was because Fred Hertrick was there. And Fred Hertrick was an ex-IBM engineer who Grant Severes had employed to design something called the RL01, which is going to be the first disk drive manufactured by DEC in Colorado. And they had made an agreement to manufacture it in DEC, and they wanted to have the engineering team near it in Colorado. And that was the RL01 removable media disk drive.
Right.
And they did not want to be in Boulder, because Storage Tech was in Boulder and they didn't want to compete. So they ended up going to Colorado Springs.
Boulder's expensive. Colorado Springs was cheap.
Went to Colorado Springs, was just far enough away so that people weren't going to probably commute it, and they weren't going to steal each other's people, but maybe DEC could get a few Boulder guys to move down to Colorado Springs, which they did.
And we recruited a lot from
California.
Cal Poly.
Oh, absolutely.
Not so much from Caltech, but a lot from Cal Poly.
In fact, I can specifically say that as the guy that ran that group for a number of years in the 80s, most of our not most, but a large number of our very talented engineers came from Cal Poly. And the reason in San Luis Obispo, because they were very practical, lab-trained engineers. They weren't just theoretical. They were very good.
So Barry had put this team together, and I started working with some people doing simulation. In fact, as a side effect, I wound up using a language called Simula, which was one of the first object-oriented languages. So I got kind of an early introduction to object-oriented software, which didn't take. I'm still not I don't consider myself an object-oriented software guy, but it was a good learning experience. And we moved out to Colorado, and we started working on a couple of things. First, we started working on some backplane storage controllers that fit into Digital's storage buses at the time. Digital had a bunch of buses out there, but there were two peripheral buses that were in common use and were kind of universal across DEC systems. One was called the Unibus, and it came out with the original PDP-11. It was an asynchronous parallel bus. And the other was called the Q-Bus, and that came out with the low-cost PDP-11s. But VAXs supported the Unibus, and I think there were adapters that you could support PDP-10s through the Unibus. I'm not so sure. PDP-10 was tended to be more something called mass bus. So we started out building a controller called the UDA-50, right, which is a Unibus disk adapter.
Right.
50 was because it was going to be the middle of some range, maybe. And we started building, as opposed to an ad hoc disk bus, usually every disk wound up with its own bus that controlled the stuff. We architected an interface to the disk drive. It was called SDI, the standard disk interface. And it started out being a parallel cable, 16 bits of transfer, and a whole bunch of control wires. And we had to fix that because one of the early prototypes, disks were big then, right? A disk drive, 14-inch platters. The whole drive was a full rack wide, and usually you could only fit about 4 in the height of a rack, and they weighed some ungodly amount, 150, 200 pounds or something like that. And so if you wanted any number of them, you had to put them in cabinets that were separate from the cabinets that you put your CPU in, and then you had to run cables out to those cabinets. And they pulled a lot of power, and the CPUs pulled a lot of power. And the first time we actually hooked up our SDI bus to a disk drive that was in a separate cabinet and plugged into a different outlet on the wall, the cable caught fire.
I hadn't heard that story.
Because
that's the
ground difference between the two cabinets, the ground wires in the cable weren't good enough, and then it was like, oh my God, we got to beef up the grounds, and we got a differential signaling, and all of a sudden this cable's becoming another mass bus cable, which was about this thick. And so one of the hardware engineers got the idea, why don't we go serial? Okay, and we knocked those many wires in a parallel cable down to 4 serial wires. And since we had a lot of parallel control signals, they were generic parallel control signals, start reading, start writing, and the drive is sending back things like sector. I saw a sector pulse, I saw an index pulse, things like that. 2 wires ran in each direction. One of them held data, and the other one held a rotating 6-bit status field, a rotating 6-bit field. Right? And we'd run these wires at the incredible speed of 25 megabits per second.
Which was very fast in those days.
Which was faster than the drives could transfer, way faster than the drives could transfer at the time in 1979.
In fact, the CDC SMD, which was a standard at the time, was at 10 megabits a second.
Right. So we thought,
and that was a parallel bus.
We thought we had plenty of margin. By the late 80s, we had exhausted that margin.
Right.
But that was as fast as we could get the stuff to go reliably, because we had to go 25 meters. Because these cabinets could be arbitrarily far apart. We didn't want to really set any hard limits on it. So the bus got redesigned to this parallel interface, and there was a chip group in VLSI, only it wasn't V, it was LSI, group in Shrewsbury under, I think, Norm Field.
Yep.
Employing guys like Bruce Book and a bunch of Mike Lease and a whole bunch of chip designers and analog guys who developed, and I wish I now remember the name of our ECC expert, because he was something. He wasn't great at communicating, but boy did he know Galois fields.
Well, we had one who was Chinese.
Yes, that's the one I'm talking about.
I'll get the name later. Li Wang.
Li Wang.
Li Wang. He was a world's expert, as was Mike Riggle.
In ECC.
But there was a couple other guys who were pretty good at ECC, including Lease.
So they designed a couple of chips to support this version of the bus. One was a SerDes that would take parallel signals and turn them into serial signals and do syncing and all that stuff on the serial bus. And the other was a dedicated chip to do the first part of ECC calculations. ECC calculations are basically solving simultaneous equations in Galois fields, but first you have to compute something called residues, which is very compute intensive. And so this chip would compute the residues, and then the software could go read the residues and go solve the simultaneous
actually
equations.
A real-time Reed-Solomon code.
Yes, it was a real-time, very sophisticated at the time. Most disks had like a 32-bit check code on an entire sector, 4,000 bits of information, 512-byte sector, and it would detect 1 or 2 bits in error. This was a 170-bit code, very sophisticated for its time, and it consisted of 17 10-bit symbols, and we could correct any 8 symbols being wrong somewhere in the sector. And the idea was that was going to give us a competitive advantage, because we could crank our density even closer to the hairy edge than other people and get more information out, and that would pay for that 4.5% overhead, roughly, that the ECC put on top of each sector, that we could crank our density by 20%.
All right, now just to get a little historical perspective, you moved out there in the summer of '78.
Summer of '78.
I know, because UDA shipped on my shift in early '82, the UDA 50. When did the decisions get made to go from parallel to serial and to a Reed-Solomon error-correcting code? Did that happen right after you got there, or
so the Reed-Solomon error-correcting code was an independent decision. That came out of the disk electronics guys saying we really need a sophisticated code, and that worked on the parallel data that came out of the SerDes. Okay. So when we made the move from a parallel bus to a serial bus, that chip basically hardly changed at all. Okay. But the SerDes was kind of was part of that. Oops.
Yep.
Parallel ain't the way to go. We got to go serial. Let's get this chip out in a hurry. And so that was, that was one of the gating items there.
Well, one of the reasons I'm asking is because that's a key piece of what became known as the digital storage architecture, which you'll elaborate on later. Bus. And it was pervasive. It was used on every disk drive for the next 10 years plus.
Right.
And
we
tape
had controllers that could mix and match disk drives across generations, across form factors, because they all corresponded to this standard bus. And before this time, there were some standard buses, but they weren't. There were things like ST506 and and a couple of others. They were pretty
SMD
low.
Had just become a standard.
They were pretty low-end buses. They didn't really work for high-performance disk drives very well.
SCSI was not yet a standard. They were working on it. It wasn't a standard.
Intelligence had
ID not happened yet
enough to push into the disk drive.
We
did have in the disk drives that were on the SDI, the standard disk architecture, They had a processor in memory, but that processor was much more like an 8080. Right? And would handle things like you'd send commands over the data lines to the drive, and you'd use the status lines to say, hey, this is a command. And the command would be like a seek, and it would consist of multiple bytes, and the drive would put it together and go, okay, I got a seek, and the microprocessor in the drive would control that. But when the data started flowing, the microprocessor just kind of ducked down and let the data fly right over its head, right onto the wires, because it was nowhere near fast enough to process that data.
Now,
and nowhere near fast enough even to control the timing of what's going on in the sector with headers and data and turning things on and off at the right time. That was done over the wires by the controller.
Now again, just again for a historical perspective, because I know Barry and I know Mike, and of course you, Riggle, that is, when did they begin to come to the conclusion that they needed a comprehensive, extendable architecture that they could repeat for multiple generations? Did that happen kind of simultaneously, or they had pre-planned that?
The idea of a standard disk bus was there before I arrived.
Okay.
So I can't really tell you who came up with it, right? It was just a given that we were going to have a standard disk bus. Digital was very big as a company into backwards compatibility, meaning you build you don't just build something, you build an architecture, and then you build members that comply to the architecture. And because you do that, the stuff that you build today will interoperate with the stuff that you build 5 years down the road. We were an architecture-driven company. That's why we built a PDP-11 architecture, and then we built like 6 or 7 implementations over a span of 10 to 1 or more of compute power. And in fact, Gordon Bell's famous dictum went on April 1st, 1975, when he started the VAX architecture group, along with the memory is getting cheaper speech. He said, I want an architecture that will cover 1,000 to 1 range, 1,000 to 1 in performance, right? And sometime around the late 80s, I went up and looked at what you could get in a VAXcluster versus what our cheapest VAX was selling for, and I sent out a memo that said, we made it. That's the biggest VAXcluster you could buy, full of, I think at the time it was maybe 8600s or maybe VAX 9000s or something like that. You could put like 16 of them out there in a cluster, and then you look at the microVAX and its performance, and it was 1,000 to 1. And Gordon got his wish.
Fascinating thing. I'd forgotten that piece. And Gordon, of course, is long gone.
So Gordon was not really involved in the storage stuff. In fact, somewhere in the middle of it, around the mid '80s, he left the company.
Right.
But he was involved at the beginning and influenced some decisions, and possibly not for the better. I can mention that.
All right, so go back again. You're now in the late 70s. The company's working on the RL01, which is a completely separate product.
That was in Massachusetts.
You're working on the first product set for the DSA architecture, the digital storage architecture, which is the UDA-50 and a Winchester drive called the RM80.
Yeah, which we were turning into the RA80. We took we started with an existing drive and just modified the front end because it minimized the amount of new stuff that all had to work.
They actually put on RM80 first, which was a mass bus version.
Exactly.
And then they put on R80,
and then we took
which
the same
was
heads
STI.
and media and servo and all that, and put a different control card in front of it, and it became the RA80. It was, if memory serves, it was like a 120 megabyte monster drive.
And that drive, 120 megabytes, right? That drive and the UDA-50 shifted. I started in August '81, and we shipped it in the spring of '82. So I know that happened. In the between that time frame, when you got there, 78, 70 to 81, when I'm familiar, the HSC was well underway. When did the concept of VAX clustering and a hierarchical storage controller that could control storage of multiple VAXs, called the HSC, when did that start?
So I can't put nearly as precise a date on that because I was a little peripheral to that. I was out in Colorado. But I do know that the genesis of VAX clusters came, as usual at that time, with Gordon. Gordon Bell.
So it was his idea.
And in this case, it wasn't a technology trend that was worrying Gordon. It was the rise of Tandem.
Makes sense.
And Tandem was building highly reliable systems. And while we
fully redundant kind of systems, what they were doing.
And they got their reliability through redundancy of separate computers. And Tandem had I don't want to put words in Tandem's mouth, but my recollection was that Tandem had a dual, because everything was dual with Tandem,
Right.
that's what Tandem means, a dual bus. They called it, I think, the X and Y bus,
Might
and
be
it
right,
connected their multiple processors together, okay? And basically Gordon said, we need something to compete with Tandem's X and Y bus.
Okay.
But because I'm Gordon and because we're digital, I don't want to just copy what they did. I want a bus that not only will give us a reliable, redundant connection between computers that we can then build a reliable system out of the two computers, or I want a reliable bus that will connect N computers together, for N to be arbitrarily big, right? Not quite, he didn't say that, but I want N to be big, right? And I want to be able to scale the compute power with the number of computers you put on this thing, as well as be completely enable fault tolerance between all the computers in this collection.
Right.
And
so that's what became known as a cluster.
That concept became the VAXcluster.
Right.
And we, at the time in Colorado, we were building these single board and two board backplane controllers, the UDA and the QDA, and they used the 2901. 2901 was a 4-bit bit slice. We put 4 of them together, so we'd have a 16-bit data path, okay, and put some EEPROM on it, and wrote code to drive that drive bus. And also on the host side, we figured we needed two things. One, we needed an interface to pass commands over to the controller. And second, we needed a command language for the controller. And so we, again, because we were digital and architecture comes first, we built an architecture to do both. We built what's called a port architecture to figure out how you pass information using shared memory from a process running on a computer to a process running on a peripheral. I don't remember if that ever had a formal name. We called it the UDA port.
Yep.
Okay, but it was basically a ring buffer in memory, and one guy would be the producer and the other guy would be the consumer, and it was very efficient. There was a little doorbell you rang after you put something into the ring, and the other guy had a little doorbell that he rung when he freed something up. And if the things got hot and heavy, you didn't have to ring the doorbell right away. You could put a bunch of guys in there, so the harder you hit it, the more efficiently it ran. And it was a nice little bus, and it later, some version of it kind of became an industry standard way to do communication, but we actually were there first and got a patent on it. And then the other thing was you needed a language to specify what you wanted the controller to do, and also to handle all the interesting bookkeeping about what drives do you own, what's their status, could you tell this drive to do this, etc. And that was called MSCP, the Mass Storage Control Protocol. We didn't want to call it a disk control protocol because we wanted to handle tapes as well with the same architecture and the same bus.
And ultimately, it also
became
took optical.
STI. We just redefined what some of the status bits meant to be tape status bits, and we used the same physical bus and the same encoding schemes and all the rest of it. So.
And again, was the MSCP evolution and stuff, was that on your time in Colorado?
That was in my time frame.
This is all happened in the late 70s.
I was a major contributor to MSCP, but I didn't own the spec. The key spec owner for MSCP was a guy named Ed Gardner. Yep. Who was very good at this kind of architectural thinking and architectural writing. Right. He was a prolific writer. The MSCP spec was a thick document, just like the SCSI spec today is an even thicker document. In fact, he wound up representing us on the SCSI committees for a while because he had that kind of experience. The port, the UDA port, was a cooperative effort. Again, I was involved and Ed Gardner was involved, and I think our names are on the patents along with Barry Rubinson and some other folks. But MSCP we never patented. It was a trade secret, I believe. So we've been developing that stuff for the UDA, and we knew that we wanted to build a big brother to the UDA, and we knew that it wasn't going to be a backplane controller, that it was going to be a controller that connected with some kind of bus to the, that was going to sit at the end of the bus because it was going to be big enough that it was going to have to be a significant hunk of a cabinet all by itself. And that controller was going to incorporate some of our real cool ideas about what to put in a storage controller. And we called that controller the HSC, which stands for Hierarchical Storage Controller. And the H part was that we were going to implement caching in that controller. Okay?
So when do you
that
think
controller was capable of having a lot of memory, and we wanted, because it was going to be an expensive box, for it to be able to handle a lot of disks.
So when did that idea flourish into basically an architectural spec by which you could start implementing it? Did you have that by, say, 1979 or 80?
Yes, we
I know it was well underway by
we actually were working on that in we were working on that when I started in 78.
All right,
it
so that was already
really
underway.
was preliminary then.
Okay.
And I got to contribute a lot to.
Right.
And because I was one of the few people in the group, there were lots of good hardware engineers in the group. There were lots of good software engineers in the group. But I was one of the few people in the group that had experience in both. Okay? I could do microcode, the kind of code that would run in those 2901 chips, and I knew what hardware could do, and I could write software as well. And so I became in charge of what was called I did a lot of coding for the UDA and the QDA, which was writing code for the 2901s. But the HSC was going to be big, and there was really no CPU that could handle the kind of stuff that we wanted to do, that could simultaneously keep 16 or 24 drives running at this low level of care that the drives needed, where you needed to turn on read gates and write gates on the drives, etc. So we built the HSC as an asymmetric multiprocessor, okay? And what happened was the HSC consisted of a central processing unit, which was a classic computer.
Little PDP-11.
Right? Well, right. This is where Gordon got to stick his oar in, and we didn't like it. We wanted to use a Motorola 68000 because it was a 32-bit machine, and it allowed us a big address space, and we had no idea how complicated our code was going to become, and we could even, and we could even have the luxury of doing some programming in a high-level language because we could waste a little memory at 32 bits, blah, blah, blah. Gordon came by and said, we got to eat our own dog food. You got to use a DEC processor. And the only DEC processor that could fit in the form factor was the LSI 11 class of
the T11,
processors.
Right? Or was the F11?
I think it was the T11.
Yeah, I think it was T11.
So we used that, and it didn't hurt us at first, but 5 years down the road, we kind of regretted it because the code was getting more complex, and we had to keep dealing with the restrictions of the 16-bit architecture.
So you basically had this little tiny,
we fought Gordon on that one, and we lost, and we should have won.
You had the T11 as a central processor running the machine.
Right.
And you had 2901s feeding all the data.
It was slow. It was
it
was around a MIPS, maybe a little less than 1 MIP. And then we had these 6 2/3, 150 nanosecond cycle time processors on cards. In fact, they were the guts of the UDA.
Right.
Okay, because we already had the code written for it that handled that bus. And we just plugged in cards, and we had a bus that the PDP-11 could send commands to these guys and receive status results back from these guys. And we also built a host controller, which we weren't sure what the host interface was going to be at the time, but we knew we needed one. And we figured whatever it was, we could handle it with this 2901 bit slice thing. And so we had a K-dot host, K stood for controller, and a K-dot disk and a P.IO, which is a programmable I.O. element that, the way we conceived it, it didn't do a lot of work. It was a traffic cop. Okay, it did some work, but it was fundamentally a traffic cop between all these other guys. And so one of the key things was we had to build what we called the hardware-software interface, where even though these K-dot disks and K-dot hosts were programmable themselves, the P.IO looked at them as pieces of hardware that did something, that just had intelligence in them, right? And we had to build that interface so that it was as low overhead as possible that the communication overhead was as low as possible. And that was the part that I tore off.
Okay.
Doing the hardware-software interface on how the central processor put work gave work to the other guys.
Now, Barry always described that as a data flow machine. Can you talk about why he called it a data flow machine and what that meant?
Yeah, I can in a way. One of the things we did was these, and everything here is comparative, and when I mention some of the feeds and speeds, any modern person's going to laugh at them. But we would have data coming in off the disks at up to 3 megabytes per second, 25 megabits. And we would also have control information that we would need to send to these processors. And the control information was in the part of these kind of structures that these processors would thread their way through to figure out what they were doing next and be able to introduce, because what we didn't want to do is say, do this, then do this, then do this, because we're telling them what order to do things in, and they have a better idea than we do about what order. So what we did is we wanted to give them a thing saying, this is all the stuff you have to do, right? Especially once you get on track, there might be multiple things to pick up on this track, right? You figure out the best order to do them in. So that was the key with creating these data structures, is to give these guys as much autonomy as possible, okay?
So between the data paths are kind of asynchronous, you got to manage them.
So one of the things we did was, because memory bandwidth was hard to come by, we built a separate bus for data. So there was the PIO and its memory bus, and they were just private. And then there was another memory bus that went out that used to communicate commands to these K-dot things.
So
and then there was a data bus, which was the highest bandwidth of all. It was a whole 13 megabytes per second you could read and write memory at. So you could have four disks transferring at once, and it was completely separate from the other buses. And so the way in some sense that it was a data flow machine is you set up these data structures, and these K-dot processors would operate off of them. And if you set up your data structures right, you could have this guy go and read information from a disk and put something on a queue, and the queue that it was told to put something on was actually a queue that the host K-dot processor would pick up and do the transfer to the host. And when it was done, the data structures told it to put something on a queue, which would wake up the central processor, and it would go, oh, well, that IO's finished. Why don't you just send the guy an end notification that it worked? Okay, so that's the sense in which it was a data flow machine,
so
there was no central place that all the control went into and then went out of. The control was distributed. The processors, all the disk processors and the host processors worked independently. They could communicate directly to each other. They could communicate to the central intelligence. And given the amount of compute power that we had at the time available to us for the amount of dollars we were willing to spend, that was pretty much the only way we could do it, and we got it to work.
So from an architectural perspective, this had to be one of the first implementations of the separation of data and control planes, and asynchronous accumulation of data streams that could be managed independently going in and out.
Yes, we were probably at that time racing the network guys, because if my network history isn't as good as my storage history, but 1978 or so was right around the time of first generation Ethernet. Before then, when you're communicating at 56 kilobaud or 1.4 megabaud, megabits on a T1 line or whatever it is, you could have the data plane and the control plane be the same. Memory was fast compared to what you could put on a network.
But this was a separation.
Probably 100 megabit Ethernet came out all of a sudden, and maybe even 10 megabit if they had switches, but they didn't.
10 was not there yet.
Right? You started to need a separate control plane from your data plane, but we needed it for disks, and so we implemented it then. So that was one. I don't know if we can claim a first there.
Well, it's got to be one of the early ones.
We were early.
It's got to be one of the early ones. Let's move up to the host side. The host bus was called the CI, the Computer Interconnect.
Okay, so now
talk about that and how it worked.
Yep. So this was the low-level result of Gordon's imperative, which is we need something that will allow us to reliably communicate between computers that's high bandwidth and scalable. Okay, and we explored several things. Again, Ethernet was coming out, in that time frame, and so we understood about the idea of just transmit and detect collisions, right? It was called CSMA-CD, I think, was what Ethernet used.
Right.
And we looked at that, and we decided that it was not predictable enough. The latency was not good enough for us, that you could get into this kind of collision chain where you keep pounding heads for a while until one guy moves out of the window of collision, et cetera. There was too much wasted space. It was great for Ethernet, where there were hundreds of guys competing on a
Plus, you
single
had
bus.
to have guaranteed connections because of storage rather than best
Yeah,
effort. Which
yeah.
you
Well,
do
I
with
mean,
messages.
you could put things
Right.
back together at the transport layer, but yeah, the fewer errors you got, the fewer reconnects you got. So we wanted something that was a little more deterministic, and we were willing to accept some restrictions. So we decided if we restricted the bus to 32, I believe, nodes on it, and this is, I wish I could tell you which guys came up with the hardware ideas. I know there was a guy named Steve Pomfret. He came out of the large computer group, who was instrumental in doing a lot of the hardware for this. But
Again,
somebody
we can
had to do
backfill
the analog signal design, et cetera, and I those names are lost in the fog of history to me. It was a very innovative thing. We wanted the advantages of point-to-point signaling, where a connection was kind of terminated on both ends, but yet we wanted a lot of people there, and we didn't want to implement a switch, because switching was expensive, and nobody understood it that well back in the late
Right.
70s. So somebody, I'd love to know who, came up with the idea of a big donut. And all the signals were AC signals. You know, they weren't DC levels. They were all AC modulated signals, and everybody's point-to-point connection would terminate at the donut. It was a big transformer.
That was called the star.
And it was called a star coupler. Okay, and you'd send energy down there, and your energy would go into the star coupler and radiate out. You know, the first star coupler was a 16-node star coupler. It would radiate out 15 different ways.
Right, so everybody got the same information.
Everybody got the same information. You even got a copy of your own information.
So
back.
that was unique.
Huh? That I'd never seen that anywhere before.
and then
I wasn't an analog guy, but that impressed the hell out of me.
How did you manage getting the right message to the right person?
Okay, so messages had an address field on them. That part was easy. The question is how you prevented guys from talking over each other.
Right.
Right? And the way it worked was that when we built an arbitration scheme, I think we even got a patent on this, that when the bus was idle, it defaulted to Ethernet-like CSMA-CD. Namely, you would send information out, and then you would listen to what came back. And if you saw your own information coming back, then you were the only guy transmitting. But if you saw garble coming back, then it meant that some other guy had stepped on you, okay? And that the message didn't get through to anybody. The difference between CSMA-CD and what we did is that CSMA-CD, people would just kind of time out and try again, right? What we did was we said, okay, when that happens, we're going to enter a more orderly regime. And so when you got a collision, you took your node number, which was a small, this is the difference between us and Ethernet. Your node number was a small number. It was between 0 and 15 for the original CI implementation. And you would count that many time intervals, and a time interval represented a round trip on the bus. So it was pretty quick. The bus was, I think, 70 meters, you know, from point to point, 35 to the star coupler.
And was 70 megabits a
so
second,
you would count your node number 3. You count 1, 2, 3, and if you haven't seen anybody transmit, then you transmit. You're clear. Okay, and so you were guaranteed to get through the second time. Okay, you could get a collision, and once somebody transmitted, everybody started counting. So if a transmission got through and somebody else had something to say and they were node number 5, they'd 1, 2, 3, 4, 5, and then they'd transmit if they haven't seen anything. So the busier the bus got, the more you got out of collision mode and into orderly transmit mode. Now the problem with that was that number 1 always has priority. If number 1 wants to say something, he'll always be able to lock out number 2, because number 2 will count 1, 2, and in the middle of 1, he'll see something on the bus and he'll go, oh shit, right? So the way we fixed that was we said, okay, instead of 16 numbers in this count, we'll have 32 numbers in the count. And the idea is every time you use the small number in the count, every time you count it to 3, The next time you had to count to 19. You had to add 16 to your number.
Oh, okay.
So guys would bounce back and forth between being in the high priority regime and the low priority regime.
So that's like
everybody
that's like a
turn.
fairness algorithm.
It's like a fairness algorithm,
Okay.
right? Everybody got a turn. And once that bus was defined, it became very obvious that we were going to use that bus to communicate with hosts. And not only were we going to use it to communicate with hosts, but we were going to use it to communicate with multiple hosts over the same set of wires. And so without knowing it, because the terminology didn't exist at the time, we were building the first network storage controller.
Right.
Right? Only the network was a digital proprietary network with some very nice properties.
And actually,
it ran at the time, what at the time was an astounding speed. It ran at 70 megabits per second. And because it had to be as reliable as the X and Y buses, there were two 70 megabit per second buses. So the total throughput, because you arbitrated for them independently, you know, any one node couldn't be sending on both at once, but 3 could be sending to 7 on one of the buses, and 6 could be sending to 4 on the other bus. And so it had 140 megabits per second of throughput, which was 14 times Ethernet. We felt real good about that. And I think it was higher than the X and Y bus too.
Oh, it was fastest thing in town at that point.
But that was the lowest level of VAXclusters.
Right.
Okay. What made VAXclusters work was not that bus, although the bus was instrumental in making it fast. I mean, later VAXclusters worked on Ethernet. When 100 megabit Ethernet came out, it was like, well, shit, you know, right? Didn't have the reliability, didn't have the predictable latency, but we got VAXclusters to work on a pair of Ethernets. What really made VAXclusters work was something called the VMS Lock Manager.
Right, talk about that.
And that was Dick Hustvedt. Okay, I
Okay,
believe that was
Dick's
all
contribution.
Dick
Okay.
Hustvedt.
Okay. Now talk about the concept of file sharing and locking, what that's all about.
So the idea was that just like in a multiprocessor, you lock to get exclusive access to something, and then when you're done, you release the lock, and you'd have these locks that were mutex locks that only one person could get through at a time, and you'd have locks that any number of readers could get through, but the minute a writer got in, everybody had to back off, and you'd have, you know, different classes of locks. And the VMS Lock Manager implemented that as a protocol, if you will, as a presentation layer protocol on top of the physical protocol of the CI bus and the logical transport layer protocol that I don't remember. I was actually one of the people involved in it, but it had some digital communication architecture, or SCA, system communication architecture.
Yes.
And it was a way of establishing a reliable connection between two nodes where things were delivered in order and the usual goodies of a transport layer, but it used some of the good qualities of the bus underneath it to implement it at a very low cost compared to, for instance, TCP IP, because the whole idea was low overhead, high bandwidth, low latency. So the lock manager sat on top of SCA, and
now,
and it was quite complicated, because what you didn't want to have is one processor being holding the lock database, because then that processor A becomes a bottleneck, and B, if that processor fails, what do? You're dead. So it was a distributed lock manager where locks there was a tree address space for locks, and you could find out who the master for a particular lock was by going down the tree, or if nobody owned it and you wanted to create a lock, well, you owned it, right? And every lock, everybody knew who owned every lock, and if that guy failed, then everybody else would get together and figure out who was going to take over the mastership of those locks. And so it was a marvelous design. I can't speak to it in detail. I didn't do it. I could just sit and admire it from a distance. And luckily, the storage controllers, did not have to participate in that. Okay, we had our own system. First, we made storage available to everybody. Every VAX on that cluster could do anything they wanted to any storage, because there wasn't a chance of two guys scribbling on each other's data, because the lock manager kept them from doing that.
Right.
In order to use a file, you had to take out a lock on the file, and then you owned that file, and you could access it. Or if you were Oracle database and did things in parallel, the two of you could access the file in common, but you'd use the lock manager to lock particular blocks of the file. It was a lovely design for what we call shared everything, lock-based multiprocessing.
So now, just to put that in perspective, you've now created the overview of an architecture that became known as the VAXcluster architecture.
VAXclusters.
In the VMS implementation. It later was implemented in other things besides VMS. But what you've now got is you've got this central bus, this CI bus, that's feathered out to up to 15 VAXs.
Right.
With this another up to 15 HSCs.
15 VAXs in an HSC, or 14 in a pair of HSCs.
And eventually,
actually, the HSCs would take up two nodes.
Right.
Because we were a fault-tolerant component
of
of a VAXcluster. We had two controllers. The drives had two SDI buses coming out of them. One went to one HSC,
Everything
one
was
went
running.
on the other HSC. The HSCs each sat on both CIs, and I once had to go up to the European Commission because somebody had filed an antitrust case on us in the European Commission, and they wanted to know what was so special about these buses. And so these are bureaucrats, right? So we had a plant in Air Scotland, and I was given a dull talk. They have, it's technical. These guys were like bored silly, but I was telling them about what happened. And in the middle of the talk, I reached behind a pillar and I had a pair of bolt cutters, like 4-foot high bolt cutters, professional bolt cutters. And I walked up to the system and I just grabbed the bolt cutters and I snipped the cable and I snipped another cable here, and everything kept running. And I said, that's what we do.
I love it.
Huh? Right?
I can see it now. So again, getting back to perspective.
Because I wasn't even in any danger of getting electrocuted with those bolt cutters, because both the CI and the SDI were AC signaling. There's no current flowing in those wires. So I just snapped them, right?
So again, getting it back in perspective, you've got multiple VAXs attached across the CI bus to multiple HSCs, each of which has got lots of disks and tapes on them.
Yeah.
And each VAX is running its own copy of VMS.
Yes.
And then on top of that is this layered, this distributed lock manager.
This distributed lock manager, and then other services that would use the distributed lock manager to provide cluster services, the clustered file systems, the clustered print service, the clustered batch service.
So they even could have multiple VAXs running on the same file, and this distributed lock manager is keeping them from stepping on each other's feet.
At that point it was up to the applications that both opened that file to use the distributed lock manager themselves. But for instance, Oracle did that on VMS, and our own database, RDB, did that under VMS. Multiple guys accessing the same file.
And that's completely unique.
No
one had done anything like that at that time.
Anything like that. That not only did we have the fault tolerance, but you could make these machines cooperate to run a bigger application than could run on any given one.
Right, in fact, you could make it look like all of VAXs were all part of a multiprocessor system running together on the one app, if you want.
Exactly. And although we eventually got it working under Ethernet, Husvet and his team, I think he was still around then, had to stand on their heads to do it because Ethernet didn't give us the guarantees that the CI bus gave us.
I think he was gone.
One of the problems when you have a big system like that is to figure out when somebody was gone, when somebody's gone, because you gotta make decisions based on a quorum, and the CI bus gave you a very reliable indication when somebody had disappeared. Right, Ethernet not so much so. When you had this membership problem, and it wound up being a guy at SRC, Digital System Research Center Lab, a guy who's since won the ACM Turing Award, a guy named Leslie Lamport, just a first-rate computer mind, to come up with the equivalent of the membership algorithm, which was at the heart of the distributed lock manager, trying to figure out who participated in decisions, to come out with a membership algorithm that worked for an arbitrarily unreliable bus like Ethernet.
Now, are you saying Leslie did this as part of the DEC team, or
no?
Did this later?
He did it as a researcher in parallel processing and distributed systems. He did it as a theoretician.
And,
It was not aimed at VAXclusters, it was aimed at the world in general. And since there's been a bunch of products out there in the world that have used his algorithm, it's called Paxos.
And was the VAXcluster the first to do it, or the
No,
VMS
no,
lab method?
the VAXcluster didn't do it.
Oh, okay. All right.
VAXcluster didn't do it because we cheated. We relied on some of the features of the hardware. And we didn't have to implement it in this unreliable general world environment. Okay? So we took a shortcut, but it was a very effective shortcut.
All right, now we got about 15 minutes left, and we're going to probably have to get back together some other later time to talk about beyond this. But I want to flesh out the story of the HSC and its capability, because there are a lot of things we haven't talked about.
And by the way, the Computer Museum has an HSC, because one of the last things I did before I left Compaq, which had acquired Digital, was ship an HSC to the Computer Museum.
All right, good. Talk about some of the features like volume shadowing and the things that HSC did from a functionality standpoint, and so how that all evolved.
Even though it was called the HSC, the Hierarchical Storage Controller, the first version didn't support a storage hierarchy. Mostly because we just could not put enough memory. The memory that we had to use to get that whole 13 megabytes a second was hot memory. We couldn't afford to put enough of it in there to make a difference. Eventually, we figured out a way to take some DRAM and really stick it densely on a board and make it, put it on those buses, the data bus and the control bus, and put a little processor on it to move data in and out of that memory. And then we did implement cache, and we did finally satisfy the H in HSC. But one of the things, obviously, when you do a reliable fault-tolerant system is you have to have reliable fault-tolerant storage. So the first thing that we did in the controller was to implement volume shadowing in the HSC. Again, shadowing, now the word's mirroring, but at the time we called it volume shadowing. And you could designate two volumes and they become part of a shadow set, and the HSC would maintain those two volumes in sync. Okay.
And that's actually what later became named as RAID 0.
That was RAID 1.
RAID 1.
RAID 1.
RAID 1.
That was just giving it a name. The
Berkeley,
Randy Katz and the Berkeley guys came up with a RAID taxonomy, and then as part of that RAID taxonomy, they kind of introduced parity RAID 5 to the world. So it wasn't just a simple act of definition, it was an act of invention as well. But in their taxonomy, the shadowing and mirroring became RAID 1. However, as VAXclusters started to move to things like Ethernet and other interconnects where we didn't have our own storage controllers, the HSC never became an Ethernet storage controller. They needed to implement shadowing without us. So two very bright guys in the VAX VMS group, a guy named Dave Thiel and a guy named Scott Davis, figured out a way to use on top of the distributed lock manager and everything. You don't want to, for instance, invoke the lock manager every time you do a write, or you'll just be issuing way too many calls. Disk drives even back then could do, I don't know, a whole 30 to 50 IOs per second, right? Yeah. Maybe more if you had a big queue, maybe 60 or 70. And times a lot of disk drives would be a lot of calls to the lock manager. You don't want that. So they figured out a way to do volume shadowing, do the asynchronous recovery, do all that stuff without having the controller involved, distributed volume shadowing. However, when there was an HSC in the mix, when you were in a VAXcluster on CI, they were more than happy to delegate that to us because it offloaded a lot of work from the CPU, a lot of data passing over the CI bus and passing between CPUs and stuff like that, and we just handled it. Okay. The other thing that we also extended the HSC to do was to handle tapes. And in fact, we would even, now that we handled disk and tapes, you could tell the HSC to go and back up a disk onto a tape. Because it was a block controller, it didn't know anything about what that disk contained. So it would just back up every single block of the disk to the tape, but you could do it without interrupting your processing on the CPU. So it was a good deal, right? Once we had an intelligent storage controller, we kind of figured out things that you could do with it. And that controller design lasted us. We shipped the first member of the digital storage architecture in. I remember it as late '81, but it might have been '82.
Oh, well, actually, the HSC didn't ship until '83.
And the
right,
the first generation, which was the UDA, and the QDA shipped shortly after that, and then the HSC 50 shipped in about '83.
It didn't have shadowing yet, though. That came later.
No, that came later, and the hierarchical part, the caching, came later. Then we implemented a couple of other, because there were some new digital backplane buses. There was a digital bus called the BI, which was done for mid-range VAXs. There was a digital bus called the XMI, which was a higher speed bus, which was done for the higher end VAXs. So we were at the time, and this changed, but I won't have time to get into it. We were a captive storage organization. We built storage for digital systems, period.
And it was essentially 100% proprietary, top to bottom.
It was 100% proprietary. We had a proprietary bus on the front end, we had a proprietary bus on the back end, we had proprietary protocols. They were either patented or trade secrets, and people tried to build knockoff stuff, and we would sue them, and I would get involved in depositions, and it was the classic proprietary 70s and early 80s model that worked so well then and stopped working in the late 80s and 90s.
It definitely was the fuel of the 80s.
We were slow to change, and it was one of the things that caused us financial difficulties and ultimately ruin.
Right, well, we'll talk about that next time we get together.
We were so proud of what we did that we'd rather do it our own superior way than the standard way.
All right, but we got about 5 minutes left, and about two things I'd like to have you accomplish in the next 5 to so minutes. Talk about some of the key guys involved in development of the HSC 50 and what roles they played.
Right.
People like Bob Bean, Barry Rubinson, those kind of guys.
Yep. So, and there are going to be names that I'm not going to remember now that I'll add.
We can fill them in later.
But Bob Bean was basically in charge of the software that went in the central processor, in the PIO.
And you named him earlier because he was part of what, the PDP-10 team?
He was the architect of RT11, the operating system for the 11. And of course, this was a PDP-11, so he felt right at home. Right, he did not use RT11 as the kernel for it. We built a kind of bare iron kernel that it ran on, because the key when building these storage controllers is you have hundreds of balls in the air at once. You got hundreds of IOs going on at once, and so you're constantly context switching as events occur between them, and you want to implement a system with minimal context switching. And so you start using things like lightweight threads and weightless threads and things like that, implementation techniques that aren't necessarily compatible with any of the operating systems that we built at Digital. And you do that because you got limited CPU power, right? So he designed he was the lead designer on the software in the PIO. I contributed a lot to was K.DISC.
Well, you basically did all the coding on the 2901s, right?
The guy who was, I at that point had taken more of a floating role, that I wasn't responsible for any one part. I was a floater, I was a utility infielder. So the guy who was in charge of the code there, I'm pretty sure, was a guy named, his original name was Michael Beckman, but he had something going on with his parents, so he married a Chinese woman named Shusha Chow and changed his name to Trenling Chow, okay, to kind of give his parents the finger. But so he was the lead software guy on the disk interface. The lead software guy on the host interface, and I might be wrong here, was a guy named Bill Grace.
That may be true.
Okay,
he definitely was involved with the UDA.
He's a good software guy, marathon runner, interesting guy. In terms of the hardware, I think the guy who pulled all the hardware together was a guy named Bob Blackledge.
Yep.
He was the Dave Rogers. He didn't do any piece of the hardware, but he had the overall responsibility for making sure that you could plug these boards in and out and they'd work. In fact, I believe that we supported the dynamic insertion and removal
Yes,
of
we
those
did.
boards. So he had his work cut out for him in terms of being able to do hot swap of boards within an HSC and things like that. Some of the other, on the controller side, I'll have to think, I'm drawing a blank. On the drive side, the electronics on the drive side, I think we had guys like Winston Sargent,
Yep.
who was working on that. And then, of course, we had Pete McLean, who actually was a pretty good guy in terms of drive design in general, knew about servos, knew about read-write, but I think he also took a role in building the SDI electronics, and I think his fingerprints are on that serial bus. His and Winston Sargent's
Yep.
fingerprints are on that serial bus, and their names are probably on the patents. I'm trying to think who else comes to mind. Barry Rubinson was kind of just an overall architect. He ran the MSCP process,
Right.
Because at some point it ceased to become our little way of getting a standard interface and became a corporate DEC standard, and various operating systems would want to add features, and we would want to add features, and so there was an actual corporate-wide architectural process. He ran that as well as some
Talk
other
about that a little
processes.
bit, because there was 3 major organizations involved, at least, in the VAXcluster. One was Colorado doing the HSC controller and everything
Right.
had to do with the controller and the DIS. The other was the VMS
The
world,
VMS group.
with the lock manager and all that, and then the rest was the CI group, which is part of the VAX group itself under Demmer. So
Right.
you had those 3 organizations.
Well, and we had more than that, because remember, we had an architecture, and there was a group in Shrewsbury that started up, and this was a little later.
Right,
This kind of
right.
overlapped with SCSI time, that we decided we needed to build a low-end
Yes, yes.
disk bus. We called it DSSI.
Right.
Digital Small Storage Interconnect.
Which was
or
a
something like
SCSI
that.
takeoff.
It was based on the SCSI transceivers and the SCSI wiring, but of course it ran the MSCP protocol. Because
And it was
we
also
were-
dual-ended.
We were digital, and we didn't really believe in standards at the time, or industry standards, right? Ultimately our downfall. And so there was a group in Shrewsbury with people like Fred Zayas and
Right.
Rich Wren and guys like that building. So they had a say in the MSCP standards. And eventually the Unix group wanted to deal with our controllers, right? Digital
Right.
was late to the party with Unix, but we eventually had several flavors, Ultrix and DEC, Unix and all this stuff. And of course, so it really was a corporate, architecture process, to the point where we had people whose full-time job was to be the caretaker of particular pieces of the digital storage architecture. So Ed
fact, you ultimately-
Gardner was to start. It passed to a guy named Sid Snyder. He was the
Right.
MSCP architect. And anything that needed to be done to MSCP, if you had a question about it, if you had a change you wanted to propose, you'd propose it to him. There'd be a process. Everybody would have to buy into it became a very cumbersome standards process, because digital was such a big organization and we had to run a cumbersome standards process. And I wound up managing the group. Alan Kotak actually moved from CPUs, et cetera, to storage at some point, and he wound up managing the architecture process.
Yes, he did.
And held the coordination meetings between the operating systems, and in fact, there was a monthly kind of storage get-together. Everybody, sometimes it was in Colorado, most of the times it was in Massachusetts, because most of the attendees were in Massachusetts, and Alan did those until the time that he left digital to join, I think, the World Wide Web Consortium. He became
Something
a
like
key
that, yeah.
architect in the W3C, and I took that over from him and ran that process. And this is where the CPU guys would say what they were doing next and what they needed from storage. The storage guys would say what they were doing next and what they needed from the CPU guys. Spirited discussions would ensue, and hopefully at some point consensus would be reached. Digital was very much a consensus company, and we'd move forward on it.
Wrap it up with just a few comments on one of the guys that was probably at the peak of this whole thing with his concepts and views, and that was Mike Rickle.
Yeah.
What was his role? And tell us a little bit about Mike.
So Mike was, and this was before I joined the group, okay, Mike was, I think, the guy who saw the need for intelligent storage. I don't know if somebody whispered into his ear,
No, he definitely
or he came
did.
up for it by himself, but he saw that if we didn't apply intelligence to storage, somebody else would and leave us in the
In
dust.
fact, they were.
And being a density, a density and read-write speed guy, as well as a general leader and thought leader, he also saw that that you could translate intelligence into better performance and better density and things like that. When everything got moving on the digital storage architecture part, Mike kind of detached from that and went more into an advanced development role, where he would lead the creation of new processes. He also, I believe, got the storage group involved, for instance, in databases.
Yes.
Which was kind of a neighboring technology that he thought we needed to work with as part of our ideas with storage, which gets into how I met my second wife, which will be a topic for another day. And in general, he drove the strategy, not so much how we should build things, but what should we build? What technology should we invest in? When the late 80s occurred, the disk industry went through this revolution, going from iron oxide to plated pure metal media, going from wired heads to thin film heads, going from all of a sudden motors started to collapse and we started to be able to do things in smaller form factors. And Mike was really the guy who took the technology stew out there, the component technology stew out there, and figured out what we were going to build.
I agree with you 100%. We're going to cut it at that point. Mike was probably the finest engineer I ever met in my life.
And he was
I gave the eulogy at his
also
funeral, and he's just a remarkable guy.
a gentleman engineer.
Absolutely.
He personified the idea of
Yep.
you can reach a consensus and drive ideas through the system without bullying anybody.
He was. Who was the guy that did the RISC processor for DEC that used to work in the storage group?
The which?
The RISC processor for DEC, the Alpha, who used to work in the storage group for Mike.
Dauberpool?
No, that's not the right one. I'll get it later.
Okay.
But at his funeral,
Yeah.
I quoted him about Mike was the finest engineering manager he ever met and why. And I don't remember the exact quote, but it was great. Anyway, we're going to break it off. We're going to have to resume this.
Yes, indeed.
To go forward from
Oh,
we're now sitting there about somewhere around 1986, and we haven't got.
I'll be back in the Bay Area
You'll be back.
in 2 weeks or so. 3
Thanks,
weeks.
Richie. It's been great.